Hello there, and welcome to Science for Sleep, where curiosity settles in beside you and science takes its time, easing into ideas at a pace that lets the mind stretch out and unwind. Tonight we're wandering into something that quietly touches every corner of the universe and yet rarely stops to introduce itself. It hums behind melting ice cubes, drifting galaxies, warm cups of tea, tangled headphones, cooling soup, found memories, and even the gentle way your breathing shifts as you settle in right now. It's called entropy, and while the word sounds a little stern, a little mathematical, maybe even slightly intimidating, it's actually one of the most relatable ideas in the whole landscape of physics. Entropy is the story of how things spread, how they mix, how they settle, and how the universe naturally leans towards certain states rather than others. But we won't rush into definitions or equations. There's no need for that here. Tonight we're simply beginning a slow walk toward understanding why the world often drifts toward disorder, why neatness takes effort, and why nothing stays perfectly arranged for long, no matter how many times you tidy it. Before we wander deeper into that, I'd love to know something simple and personal. Where are you listening from tonight? What does the room around you feel like? Is it quiet? Or can you hear distant sounds drifting in from the world outside? And what time is it for you right now, in your own little corner of the day or night? I always find it strangely comforting that people tuning in might be scattered across sunrise, midnight, afternoon, or something in between. All of us meeting here, in the shared moment, even though clocks and calendars might disagree about what this moment actually is. If this slow exploration feels soothing to you, or if the calm unfolding of ideas helps soften the edges of your day, I'd be grateful if you'd like the video, maybe subscribe, or share this space with someone who might appreciate a quiet pause as well. A small gesture from you helps this sleepy corner of science drift a little farther into the world, reaching the people who need something gentle to unwind with. No pressure at all, just an invitation offered lightly, the way you might pass along a cozy recommendation to a friend. Entropy is one of those rare concepts that connects the everyday world with the grand scale of the cosmos. You don't need to be a physicist to notice its effects. You can see hints of it in the way a hot drink cools down on a countertop, or how a once fresh stack of papers slowly shifts into uneven piles, if left untouched long enough. You can watch it at work when warm air spreads through a room, or when two liquids blend until their colours lose their sharp boundaries. It shows up in the odd way that things fall apart more easily than they come together, or how a drop of food colouring disperses through water without any help at all, turning the clear glass cloudy with swirling threads that eventually settle into a uniform mix. You never see the reverse happen. The colouring never gathers itself back into a tidy droplet. There's something about the natural motion of things that nudges systems toward mixing, spreading, equalizing. And while that might feel like a simple observation, it turns out to be one of the most important themes running through the fabric of reality. Part of the gentle wonder of entropy is how it sits quietly in the background, shaping outcomes without insisting that you pay attention. The universe isn't trying to be dramatic about it. It's simply following tendencies that arise from the way energy and matter behave when they're left alone. Over time, things shift into states that are more probable, more accessible, more relaxed in a sense. Highly ordered arrangements don't hold themselves together automatically. They need support, maintenance, and sometimes constant intervention. Without that, they loosen and drift because there are far more ways for something to be unarranged than perfectly arranged. A neatly made bed has only one configuration that counts as tidy, but countless ways to look wrinkled or uneven. A deck of cards has one exact ordering when sorted, but an enormous number of ways to be shuffled, so the world tends to land in the states that have more options simply because they're easier to fall into. That gentle leaning toward disorder isn't a flaw in nature, it's a natural consequence of probability, and this is where entropy begins to hint at something deeper, something that connects the mundane with the cosmic. It links the melting of ice in your drink with the evolution of stars. It ties together the cooling of the early universe with the warmth of your own body. It influences weather patterns, chemical reactions, and even the way memories arrange themselves in your mind over a lifetime. But for now, we're not trying to solve any grand mysteries. We're simply letting the concepts settle in, the way a thought lingers before forming into something clearer. When people first encounter the word entropy, they often picture chaos, collapse, or everything drifting toward ruin, but that's not the heart of it. Entropy isn't about destruction. It's about movement and distribution. It's about how energy refuses to stay concentrated in one place. It's about how systems drift toward balance, how temperatures equalize, how structures loosen unless effort is applied, and how the universe uses up pockets of order in the process of shaping new forms. That doesn't mean everything fades or falls apart. Far from it. The same principle that encourages mixing also allows stars to ignite, planets to form, life to emerge, and complexity to arise. Entropy doesn't halt creativity. It guides the conditions that make creativity possible. When you set a hot mug down on a cold surface, heat doesn't stay neatly contained inside the mug. It spreads into the air and the table, dispersing itself because there are many more ways for heat energy to spread than to remain concentrated. The difference in temperature smooths out. The system relaxes. And while that relaxation might seem like something fading, it's actually a form of movement. Energy continues its journey, flowing into states where it can be shared rather than held tightly. That flow underlies countless processes in nature, many of which feel intuitive once you think about them. A drop of perfume diffusing through a room doesn't need guidance. A warm breeze drifting into cool air doesn't require a push. These transitions simply happen because the underlying rules encourage them. You can see similar patterns at larger scales. A star radiates heat and light because energy stored in its core naturally spreads outward as nuclear reactions release it. Over time, stars exhaust their fuel and cool, but not in a sudden collapse. They transition through stages guided by the same principles that help warm air rise and cool air sink. Entropy shapes the grand arcs of stellar lifetimes, just as it shapes the cooling of the cup on your desk. And though these events unfold on wildly different timescales, the undercurrent is the same. Systems evolve toward conditions where energy is more evenly spread out, but entropy doesn't have to be thought of as something that makes the world fall apart. It also plays a role in the creation of patterns. Consider how clouds form. Water molecules float in the air, colliding, bouncing, shifting, and then gathering under the right conditions into visible shapes. The clouds themselves are temporary and constantly changing, but their formation reflects a balance between order and disorder. Entropy drives the spread of water vapor, but temperature and pressure help guide those molecules into patterns we find familiar. Many natural forms arise from this interplay between spreading and shaping. Sand dunes, weather systems, ocean currents, and even the branching structures of trees and rivers all emerge from this balance. Entropy provides the push that keeps everything moving, and other forces provide the structure that channels that movement into forms. As you listen, you might start to notice echoes of entropy in your own life. It shows up in routines, habits, and even the way tasks seem to scatter if left unattended. A cluttered desk doesn't require any effort to create. It forms slowly, one absent-minded placement at a time. But tidying the desk requires intention because you're moving the system into a less probable arrangement. Most of the time, objects drift toward where they're used, not where they're stored. It's a small, everyday example of how effort is needed to maintain low-entropy states. This isn't a cosmic judgment or a moral principle. It's simply how systems behave when they contain many components that can be arranged in many different ways. Even your own body follows entropy's guidance. The warmth you radiate into the surrounding air, the way your breath mixes with the room, the way nutrients break down to release energy that your cells use. Each process follows the same gentle principle of spreading and balancing. Nothing needs to be forced. The systems are built to follow paths that naturally allow energy to move from concentrated forms to ones that disperse. And somewhere within that movement, within that continuous shifting, life finds its rhythm. Entropy can also help explain why certain processes feel irreversible. When cream mixes into coffee, the swirling patterns gradually fade into a uniform colour, and the mixture doesn't spontaneously reseparate. The system has moved into a state with far more possible arrangements than the original neat layering. That doesn't mean the world becomes less interesting as things mix. It simply means the system settles into a condition where its components have more freedom to move. A balanced state isn't empty, it's simply different. And understanding that difference can make entropy seem less like an agent of decay and more like a quiet guide to how things unfold. As we keep moving forward, we'll continue exploring different sides of entropy, from the small-scale details to the vast scale of the universe, not in a rushed way, and not with the urgency of trying to solve everything at once. Just a slow, steady continuation, letting each idea build on the last so the whole picture grows clearer without needing to force it. The beauty of this topic is that it doesn't require memorizing formulas or gripping tightly onto jargon. It's about noticing patterns that were always there, patterns that help explain why the world behaves the way it does. And little by little, each part of this exploration will add another piece to that understanding, giving you space to wander through the idea without pressure. There's something quietly intriguing about the way disorder appears in the world, not as an enemy or a flaw, but as a natural outcome of things simply being allowed to move, interact, and shift without guidance. When people hear the word disorder, they often picture chaos, messiness, a sense that things have gone wrong somewhere. But in the context of entropy, disorder isn't some dramatic collapse or a sign of failure. It's something more subtle, more everyday, and strangely, more comforting once you start noticing it in the right light. Disorder isn't an accident. It's an expected part of how systems evolve when countless small elements interact freely without strict instructions. And understanding that can bring a surprising sense of calm to the way we observe the world around us. When you take something simple, like a handful of beads, and drop them onto a table, they don't arrange themselves into neat lines or symmetrical patterns. They scatter. Not because they're misbehaving, but because scattering is the most natural outcome when there's nothing nudging them toward a more structured arrangement. The scattered state has far more possible configurations than the tidy state. The same beads could land in countless positions. A perfectly aligned pattern has only one or two precise ways of existing. So the disordered state isn't something unusual or unruly. It's the most probable one. That quiet leaning toward disorder is what entropy helps us understand, not just in beads or sand or air molecules, but in every process that involves energy, motion, and interaction. If you watch dust drifting in a sunbeam, tiny particles dancing in the air, their movement looks random. But that randomness is actually the collective result of countless collisions with invisible molecules of air. Each dust particle is nudged from all sides, never receiving enough coordinated force to settle into an ordered path. The result is a movement pattern that seems unpredictable, but it arises naturally from the many possible ways the molecules can push and pull on it. This simple observation helps illustrate what disorder really means in entropy. It's not a lack of rules, it's the presence of many possible states, each equally allowed by the underlying physics. The system isn't confused, it's free. Even something as ordinary as a stack of papers shifting slightly over time reflects this tendency. The papers don't spontaneously line themselves up at perfect right angles. Instead, small vibrations from footsteps, air currents, or gentle handling allow them to drift minutely out of alignment. Over time, these small motions accumulate, and the perfectly ordered pile becomes less so, not through some sudden collapse, but through gradual settling into states with more possibilities. Perfect alignment requires continuous attention, because it represents a narrow target. Disorder requires no effort because it encompasses countless arrangements. Entropy helps explain why the latter is the fate of any system left to itself unless energy is invested in maintaining structure. When you sit with the idea that disorder is simply the natural resting condition for most systems, a lot of familiar experiences start to make more sense. A cup of hot water cooling to room temperature is not a system declining. It's a system moving from a state with energy concentrated in one small area to a state where energy is shared more broadly. That shared state has many more possible configurations than the original, highly focused one. Disorder in this sense isn't messy. It's evenly spread out. Hot becomes warm, then becomes the same temperature as everything else, not because warmth is better in any philosophical sense, but because it offers so many more microstates for the molecules involved. And that simple truth quietly shapes everything from cooking to weather to the distant behaviour of stars. The idea of disorder as something natural also helps remove the stress people sometimes feel when trying to keep their surroundings perfectly arranged. A room that collects small signs of use, objects slightly out of place, cushions that shift when sat on, or items that gradually scatter around the surfaces isn't evidence that things have gone wrong. It's evidence that a room is being lived in. The effort of maintaining order is just that. Effort. Bringing items back to their assigned positions requires energy, because you're coaxing the system into a less probable configuration. Once you see that, it becomes easier to appreciate that disorder isn't a personal failing or a sign of chaos. It's simply what happens when energy isn't constantly spent to keep things aligned. This natural tilt toward disorder becomes even more interesting when you look at fluids. Pour a drop of dye into water, and the colour spreads, turning the clear liquid into a gentle swirl before settling into an even tint. At first glance, it might seem like the dye loses its structure, drifting from a clean droplet into something mixed. But what's actually happening is that the dye molecules find a vastly larger number of possible positions when dispersed. They're not becoming chaotic, they're becoming distributed. The spread isn't a breakdown, it's a shift into a state with far more ways to exist. And that shift, once again, arises effortlessly, because the underlying rules make it easier for molecules to wander than to cluster. You can also see disorder in the way heat naturally flows from warm regions to cooler ones. If you place your hand near a warm mug, you can feel the heat spreading out. It doesn't stay contained because the concentrated state is not the default. The natural movement is from order to disorder, from localized energy to shared energy. And that movement supports the processes we often take for granted. Weather systems rely on temperature gradients. Ocean currents follow similar principles. Even the way air circulates through a room, evening out temperature differences near windows, doors, and corners, shows how disorder helps create balanced environments. The world isn't falling apart when these shifts occur. It's following patterns that, when you step back, look beautifully consistent. There's a subtle clarity that comes from noticing how systems lean into disorder without needing instructions. A box of mixed nuts, when shaken, doesn't sort itself into neat sections. Instead, smaller pieces slide to the bottom, larger ones rise, and everything finds a loose arrangement. This isn't a rejection of order. It's the consequence of movement paired with variation in shape and size. The system is responding to gravity, collisions, and space in ways that produce outcomes that might seem disorderly, but are actually predictable from the standpoint of probability. Disorder is the range of outcomes that doesn't require precision. It's the default because it demands nothing beyond the natural interplay of components. The idea becomes even clearer when you think about gases. Gas molecules move freely, colliding and bouncing without any rigid structure. If you release gas into a container, it spreads evenly throughout, not because it was instructed to fill the space, but because each molecule has countless possible positions it can occupy. The spread is the most probable distribution. If all the gas molecules gathered in one corner of the container, that would still technically be allowed by the laws of physics, but it's extraordinarily improbable because it represents only one of many possible configurations. The more components a system has, the more overwhelming the number of disordered states becomes, and the more naturally the system drifts toward them. Disorder also helps explain why certain systems feel stable, even when they're constantly moving at the microscopic level. When you hold a cup of room temperature water, the molecules inside are in motion, colliding, exchanging energy, and shifting positions. But because the energy is distributed evenly, the system as a whole has no reason to change in any noticeable way. It's not frozen or stagnant, it's simply settled into one of its most probable states. If you warm the water, you're lifting it into a less probable condition by concentrating energy. Once that energy begins to spread again, the system relaxes back into disorder. Not a collapse, but a return to equilibrium. People sometimes think of disorder as something humans must avoid or correct, but many of the most functional systems rely on it. Consider the way your lungs operate. Air doesn't organize itself neatly before entering your body. It flows in, mixing freely, and oxygen molecules spread through the alveoli because there are countless pathways available to them. The distribution happens through diffusion, a process that relies entirely on the natural movement toward disorder. Your bloodstream carries oxygen to cells that require it, and carbon dioxide flows outward in the opposite direction. These exchanges rely on the same principles of energy distribution and molecular freedom. Disorder in this context isn't a hindrance, it's essential. The same is true for countless cellular processes. Inside each cell, proteins, ions, and molecules move through spaces where their interactions are guided by probability. They don't arrange themselves neatly. They drift, meet, bind, release, assemble, and transform in ways that take advantage of the fact that the system contains many possible configurations. The cell isn't a tidy factory with perfectly arranged components. It's a dynamic environment where disorder enables the necessary interactions to occur efficiently. The apparent messiness is actually a reflection of the system working exactly as it should. If you look at larger structures like ecosystems, you see similar patterns. Animals move through environments in ways that spread seeds, shape growth patterns, and promote variety. Not through rigid organization, but through countless interactions that aren't centrally controlled. Disorder doesn't mean the system is unstable. It means there are many possible ways for life to arrange itself, and that flexibility supports resilience. The variety of configurations gives ecosystems the ability to adapt without requiring perfect coordination. Even human society reflects this principle in subtle ways. Crowds, traffic, communication networks, and marketplaces evolve through numerous small decisions that overlay one another. While it might seem disordered, that very looseness allows systems to function without collapsing under the burden of rigidity. There are many ways for interactions to occur, and that multiplicity creates stability through flexibility. Once again, disorder isn't something broken, it's something that expands possibilities. Thinking about disorder through the lens of entropy helps remove the weight people sometimes attach to the idea. Disorder isn't a flaw. It's a natural state of freedom within systems. It shows up in heat flow, molecular movement, ecological patterns, and even the subtle ways your body maintains balance. When you look closely, disorder appears less like a problem and more like the space within which patterns can form, evolve, and function. There's a quiet comfort in realizing that the universe's preference for messiness isn't a judgment or a flaw, but a natural outcome of how things behave when they're left to follow their most accessible paths. When people first learn that entropy tends to increase, and that systems move towards states that look disordered or scattered, it can create a sense that nature is somehow biased toward things falling apart. But that's not really the story. The real story is that the universe is guided by probabilities, and the paths that lead to what looks like messiness are simply the most available ones. They require the least effort. They offer the most freedom. And they emerge from the straightforward fact that there are far more unstructured arrangements than structured ones. Thinking about it through probability helps remove the drama from it. Imagine a deck of cards sitting neatly sorted, suits aligned, numbers in perfect order. That arrangement is possible, but it represents only one precise configuration. If you shuffle the deck thoroughly, the chances of returning to that exact order are astronomically tiny. Not because the universe resists order, but because a perfectly sorted deck is just one outcome among an enormous number of possible ones. A shuffled deck has no special resistance to being sorted. It's simply more likely to be in one of the countless mixed states than in the one single ordered one. The same principle extends far beyond cards. Molecules, energy, temperature, and matter all follow the same statistical tendencies. If there are many more ways for something to be dispersed than condensed, the dispersed state wins out by sheer probability. When heat spreads through a system, the outcome isn't chosen intentionally. Warm regions lose energy to cooler ones because the energy isn't confined. It can move in many directions, collide with many particles, and distribute itself more evenly simply because there are countless ways to share energy across a system. The evenly spread state has far more possible configurations than the concentrated one. If you think of each microscopic arrangement as a tile in an enormous mosaic, the mosaic of ordered arrangements is tiny, while the mosaic of disordered arrangements stretches across an enormous expanse. So when energy begins moving freely, it doesn't seek disorder for its own sake. It just moves into the spaces with the greatest capacity for variation. This idea becomes clearer when you look at how gases behave. When gas molecules are released into a larger space, they spread out almost instantly. They don't gather in a corner and stay there. The spread isn't rebellious. It's simply the outcome of each molecule having access to a wide range of positions. The probability of them all drifting back into a small region at the same time is vanishingly small. Not impossible, but so improbable that you could wait longer than the age of the universe and still never witness it. The messy state is simply the one with more room for the molecules to occupy, so the universe prefers it, only in the sense that it is the overwhelmingly probable configuration. What might look like messiness is often just a system settling into a state where no particular arrangement is privileged. A tidy state singles out one specific pattern, while a messy state includes a broad range of patterns that don't require precision. Once you frame it that way, the universe's behaviour feels less like a drift toward decay and more like the natural settling of systems into the widest landscape available to them. You can even see this in something as unassuming as popcorn. When you first pour kernels into a pan or a machine, they're arranged in a reasonably structured pile. As heat is applied, each kernel absorbs energy, builds pressure internally and eventually bursts. Once popped, the pieces no longer resemble their original arrangement. They scatter and shift because there are many more ways for fluffy pieces to land than for compact kernels to stack neatly. The end result might look messy, but it's simply an expression of the principle that more configurations are accessible after the energy input than before. The mess isn't a collapse, it's a natural expansion into possibility. The same reasoning helps explain why objects cool down rather than heat up spontaneously. A hot object has concentrated energy. That concentration is a low entropy state, not because heat is inherently orderly, but because the specific arrangement of energy that creates a temperature difference is relatively rare. When energy begins transferring from the hot object to its surroundings, the system gains access to more microscopic configurations. Once again, the shift to messiness isn't a downward slide, it's a broadening of options. If the system were to spontaneously become hotter, concentrating energy in one place without external input, it would be moving into a narrow zone of possibility with fewer accessible configurations. Nature doesn't forbid that, but the probability is so small that it's practically non-existent. The universe isn't resisting heat flow. It's accommodating the far more likely outcome. This probabilistic view also explains why large structures like galaxies can emerge even in a universe that tends toward increasing entropy. While clustering might sound like a decrease in disorder, The processes that lead to galaxy formation involve massive gravitational interactions, energy flows, radiation, and dynamic changes. The universe's initial conditions allowed for large-scale clumping while still following the overall trend toward higher entropy. The growth of complexity is not opposed to entropy. It is made possible by localized temporary decreases within the broader backdrop of spreading energy. Stars shine by converting concentrated energy into dispersed radiation. Life uses energy to build structures while increasing disorder in its surroundings. Complexity arises not despite the universe's preference for messiness, but within it. If you think of entropy as a measure of how many possibilities a system has, the preference for messiness starts to look like something neutral and steady rather than destructive. The universe isn't leaning toward collapse, it's leaning toward abundance. Abundance of accessible states, abundance of ways to distribute energy, abundance of pathways the system can follow. A structured state is a narrow path through a forest. A disordered state is an open field. When systems move, bump, exchange energy, or change shape, they naturally wander through the open field more than the narrow path simply because there's more space to occupy. This subtle preference appears in places you might not expect. Think about the way two liquids mix. Pouring milk into coffee creates swirling patterns for a few moments, but those patterns fade as the liquids mix into uniformity. The fading doesn't signal disappearance of structure. The structure is still there at the molecular level, but it's dispersed among countless microscopic configurations. The mixed state corresponds to a huge number of possible arrangements of molecules, far more than the state where the milk sits in a neat layer on top. So the universe isn't choosing disorder, it's simply allowing the system to inhabit the vast region of possibilities that mixing unlocks. This idea scales up to larger systems too. Weather patterns might look chaotic, and in many ways they are, but they follow physical rules that channel air, heat, moisture, and pressure around the planet. The apparent disorder comes from the enormous number of possible configurations that the atmosphere can take on. A completely still planet with perfectly uniform temperatures and identical conditions everywhere represents an extremely ordered state with almost no freedom for movement. Real weather, with all its variability, occupies a much larger set of possible states. That's why weather is dynamic. There are many ways for air to move, clouds to form, and temperatures to shift, and the system explores those possibilities naturally. Even something mundane like laundry fresh from the dryer illustrates this tendency. The clothes come out jumbled not because tumbling them is inherently messy, but because each garment has many ways it can twist, fold, bend, and fall. A perfectly folded shirt represents one specific arrangement of its fabric. A wrinkled one represents countless possibilities. When energy is applied to the system through tumbling, heat, and motion, the clothes settle naturally into the region of configurations with more options. The universe isn't rejecting tidiness, it's simply following the statistical distribution of states. There's also a human aspect to the way messiness emerges naturally. When people walk through a room, they shift air currents, move items slightly, stir the environment just by being present. Shoes pick up dust and redistribute it. Chairs shift when someone sits down. Object placement becomes influenced by convenience, mobility, and subtle interactions. In a lived environment, perfect order requires continuous effort because the natural motion of daily life inevitably introduces small changes that accumulate. Those changes aren't mistakes. They're the natural byproduct of systems where many small movements can happen without resistance. Understanding that the universe prefers messiness because it has more ways to express itself can even change the way you view your own thought processes. The mind holds memories, impressions, sensations, and reactions that shift and spread over time. Thoughts wander not because the mind is flawed, but because there are countless pathways neural activity can take. Concentrating on one precise thought requires effort, while drifting among many possibilities happens naturally. The brain is a system with enormous freedom. where patterns form through experience, repetition, and focus, while everything else floats freely in the background. It's not unlike a gas spreading through a room. The pathways of least resistance are the ones with more accessible configurations. This broad preference for messiness can even be seen in how nature shapes landscapes. Rock formations erode unevenly because water, wind, and temperature changes act on surfaces in countless small ways. Over time, the structures that require the most precision to maintain their form break down first, while rough textures, scattered fragments, and mixed materials endure because they represent states that can be achieved through many different processes. A perfectly smooth rock surface can be marred by a single drop of water, but a jagged one can withstand thousands of drops without noticeably changing. Messiness isn't fragility, it's flexibility. You can even see the universe is leaning towards states with more possibilities in how light and heat travel. When energy radiates from a source, it spreads outward, filling space because that outward movement represents a huge number of possible paths. If the energy were to remain confined indefinitely, its configuration would remain limited. But spreading allows the energy to occupy a vastly larger number of states. This behavior drives countless processes, from the light emitted by a candle to the radiation that fills the cosmic microwave background. The universe's preference for messiness is the same principle at play in both. The large-scale patterns of the cosmos and the small-scale interactions in your own home follow similar statistical tendencies. Even the growth of crystals, which appear orderly, relies on processes that begin with disorder. Molecules in a solution move chaotically, bumping and drifting until they find themselves in positions where bonding is favourable. Only then do structured patterns emerge. Behind every orderly crystal is a population of molecules exploring countless options until the right configuration becomes stable. Without the underlying messiness of molecular motion, the crystal could never form. When you look at all these examples together, a clear pattern begins to emerge. The universe doesn't push systems toward messiness because disorder is better. It allows systems to explore the full range of possibilities available to them, and that range is overwhelmingly larger in states that appear disordered. Messiness is the wide-open landscape. Order is the narrow ridge. Both exist, both matter. But one is simply more likely because its range of configurations is so vast. This understanding doesn't make the universe feel chaotic. It makes it feel consistent, predictable in a broad sense, even if the details vary. The drift toward higher entropy is not a collapse. It's an expansion into possibility. There comes a moment, once you've grown familiar with the quiet presence of disorder and the natural ease with which systems drift toward messier states, when it becomes helpful to hear from the principle that ties all these tendencies together, not through a dramatic announcement or a heavy-handed explanation, but through a calm recognition that one law sits quietly at the center of these behaviors, guiding them gently and consistently. People sometimes imagine physical laws as stern authorities laying down strict demands about how things must behave, but that really isn't the tone of this one. The second law of thermodynamics doesn't slam doors or issue commands. Instead, it murmurs through the background of every process, shaping the way energy moves, how heat drifts, how systems settle, and how everything from stars to boiling kettles follows the same underlying direction. Understanding this law doesn't require memorizing complex formulas or mastering technical definitions. In this slow, relaxed setting, it's enough simply to explore the way it manifests in familiar experiences. The second law states that in any natural process, the entropy of a closed system will tend to increase or remain the same. That phrase might sound stiff at first, but behind the formality is an idea you can see in every part of life. Energy spreads, temperature differences fade, systems evolve towards states with more possible configurations, and these tendencies aren't rigid or abrupt. They unfold naturally, steadily, almost quietly. as though the universe prefers pathways that don't require fine-tuning or careful maintenance. It helps to think of the second law not as a rule that forces processes in one direction, but as an observation about which paths are overwhelmingly more probable. When you release a warm puff of air into a cool room, it doesn't stay bunched up. It blends. Not because blending is mandatory, but because the number of possible ways for energetic air molecules to spread is enormously larger than the number of ways to keep them together. The second law whispers that systems move toward the arrangements that give them more room to explore. That trend in turn shapes everything connected to energy flow. Consider something as simple as ice melting. If you place an ice cube in a bowl of warm water, the cold, rigid structure of the ice doesn't hold out indefinitely. The molecules in the ice are tightly arranged, each with limited ways to move. The water molecules around them, carrying higher energy, bump into the ice repeatedly. These collisions disrupt the structure until the cube begins to loosen and dissolve. The rigid arrangement melts because the combined water and ice system gains access to more possible configurations when the boundary between states disappears. The second law quietly guides this process by nudging the system toward the condition with greater freedom for its components. Nothing is pushed or forced. The ice simply yields because the alternative offers far more available arrangements. The same thing happens when you heat a pan on a stove. Energy flows from the burner into the metal, increasing the motion of atoms. If the heat source is removed, the pan doesn't remain hot for long. It cools as the energy diffuses outward into the surrounding air. The second law doesn't require the pan to cool. It simply reflects that there are significantly more microstates in which the heat is shared among the environment than confined within the metal. The system drifts naturally toward that more probable configuration. You can warm the pan again by adding energy, but maintaining that temperature requires continual input. Without it, the system relaxes back into equilibrium, following the tendency the second law describes so reliably. If you think of systems settling the way people settle into comfortable resting positions, the second law becomes even more relatable. A highly ordered state is like an awkward pose that demands effort to hold. A more disordered state is like a relaxed posture where muscles can let go. The universe doesn't care about neatness or optimization. It simply eases into configurations that require fewer constraints. Highly structured states demand constant support. Looser states can persist without supervision. The second law reflects this quiet preference for states that don't require precise coordination. What makes the second law especially interesting is that it doesn't limit its influence to one scale. Whether you're looking at microscopic particles or immense celestial bodies, the same principle shapes the direction of natural processes. It's the second law that explains why heat flows from hotter regions to colder ones, why pressure differences equalize, why gases expand, and why mixing happens so readily. It describes the broad pattern behind every process that involves the distribution of energy. And because everything in the physical world involves energy in some way, the second law reaches into every experience, even ones you wouldn't immediately associate with thermodynamics. You can see the second law at work in the way your body maintains its temperature. Your cells generate heat through metabolic processes, and that heat spreads outward, radiating into your surroundings. You don't store heat indefinitely, and you don't spontaneously become warmer without input from food or your environment. Your temperature remains stable because your body regulates itself actively. But whenever active regulation stops, the natural drift toward equilibrium resumes. Without energy being consumed to maintain order, the system slides into the more probable distribution described by the second law. If you place your hand on a cool table, warmth flows into the surface. If you wrap yourself in a blanket, you reduce the rate of heat loss, but the second law still governs the movement of energy within the enclosed space. Every breath you take carries heat away. Every surface you touch shares warmth. Energy doesn't stay confined. It moves along pathways that follow statistical likelihoods. Even processes that seem unrelated to energy distribution follow the same underlying principle. Consider the way different species spread through an ecosystem. Animals don't arrange themselves in perfect patterns. They disperse according to available resources, terrain, climate, and chance interactions. The result is rarely a tidy distribution. Instead, populations settle into complex patterns that reflect the many possible configurations of movement, reproduction, and survival. The second law isn't directly dictating these patterns, but the same concept of increased possibilities applies. Systems that evolve under many influences without strict control tend to spread into states, with larger numbers of accessible configurations. Ecosystems aren't governed by thermodynamics alone, but the logic of entropy echoes in them. The second law also explains why no engine, no matter how advanced, can operate with perfect efficiency. When you convert energy from one form to another, some of it spreads out in ways that can't be fully harnessed. Heat leaks into the environment. Motion generates friction. Electrical currents encounter resistance. These losses aren't flaws in the machines. They're reflections of the fundamental reality that distributing energy always involves some spread into less usable forms. The second law ensures that no process can be perfectly reversible. Every conversion leaves a trail of increased entropy somewhere, even if the system is engineered with incredible care. Humans can create remarkable technology, but they cannot escape the statistical nature of energy flow. When you hear all of this, it might be tempting to picture the second law as a principle that pushes everything toward decline, but that isn't the right way to interpret it. Decline implies loss of function or value. The second law deals only with the number of available microstates in a system. A state with higher entropy isn't degraded, it's simply more probable. Hot and cold balancing out isn't decay, it's equilibrium. Energetic interactions becoming more distributed isn't destruction, it's natural settling. And in many cases, increases in entropy make complex processes possible. A star shines because nuclear fusion produces high-energy photons that quickly spread outward, increasing entropy dramatically. That spread is what allows light to reach planets. Without the second law, stars wouldn't radiate. Their energy would remain confined, preventing the vast array of astrophysical phenomena we rely on for warmth and light. Life itself appears to contradict the second law at first glance, because living systems maintain organized structures, but they do so by consuming energy and increasing entropy in their surroundings. A plant doesn't grow because entropy decreases. It grows because it uses sunlight, water, and nutrients to build order, while releasing energy as heat and chemical byproducts. The overall entropy of the combined system still increases. The second law isn't violated. Life demonstrates how local pockets of order can form while contributing to increased disorder elsewhere. The whisper of the second law still guides the overall balance. Even the formation of planets and stars follows thermodynamic principles. Dust clouds in space collapse under gravity, forming hot, dense regions that eventually ignite nuclear fusion. As the cloud collapses, gravitational potential energy converts into heat, which radiates outward. Although the collapse looks like a decrease in disorder because matter concentrates, the radiation released increases entropy on a larger scale. The second law remains intact. The processes that build structure do so within the broader trend of energy becoming more dispersed. The second law's presence in these grand structures helps highlight its quiet consistency. No matter how complex a process becomes, it still reflects underlying principles that hold firm across the universe. A cup of tea cooling on a table and a star emitting light into space follow the same fundamental direction. The scale differs, but the statistical tendencies remain the same. The second law is not a restriction, but a description of the natural unfolding of events. People sometimes wonder whether the second law is absolute or if there are exceptions. In theory, microscopic fluctuations can create brief, tiny decreases in entropy. A group of molecules could momentarily cluster in a way that reduces disorder. But these events are incredibly short-lived and occur on scales too small to affect macroscopic outcomes. On the large scale that defines our everyday experience, the second law holds with a reliability that borders on certainty. These fluctuations don't violate the law. They exist within its framework, allowed but statistically insignificant. Another important aspect of the second law is its role in defining the arrow of time. Many physical laws can run forward or backward without contradiction. If you filmed 2 billiard balls colliding and played the video in reverse, the physics would still make sense. But a video of ice melting in reverse, a puddle spontaneously forming a perfect cube, would instantly seem wrong. The second law gives direction to time by making one direction overwhelmingly more probable. That direction isn't imposed, it's simply the path with more possible microstates. This deeply intuitive aspect of the second law explains why certain processes always feel one way. You can scramble an egg easily, but unscrambling it spontaneously would require the system to fall into an extremely precise arrangement of molecules out of countless random possibilities. The second law doesn't forbid the reverse. It simply makes the forward direction almost guaranteed. People often think of entropy as enforcing irreversibility. In truth, irreversibility emerges from the enormous imbalance between ordered and disordered configurations. What makes the second law so elegant is that it describes not only what will likely happen, but why it happens. It connects the microscopic world with the macroscopic one. It bridges probability with physical behavior, and it does so without dictating rigid outcomes. Instead, it gently guides processes towards states with more flexibility, more room, more options. This perspective can also help soften the way people think about change. When things shift from structured to less structured states, it doesn't always signify loss. Sometimes it indicates that a system is relaxing into a natural distribution of energy in a matter. Not everything is meant to remain perfectly arranged. The universe grows, evolves, mixes, disperses, and transforms, not through disorder for disorder's sake, but through the simple mathematics of probability. The second law doesn't hurry anything along, it just makes the most likely outcome steadily unfold. When you think about this law in the context of daily life, it stops feeling like an abstract scientific principle and begins to resemble something familiar. Every cooling cup, every drifting scent, every spreading ripple follows the same quiet guidance. Energy never vanishes. It simply finds new ways to distribute itself. The second law doesn't shout its presence. It operates quietly, consistently, and without fanfare. Its whisper is the background rhythm of countless processes happening around you and within you. Most people don't realize how wide the reach of entropy really is. It isn't confined to laboratories, dusty textbooks, or rare conditions hidden inside scientific equipment. It shows up in places so ordinary that you barely notice its presence, and at scales so enormous that entire galaxies follow the same tendencies. The remarkable thing is that the same principle guiding a melting ice cube on a kitchen counter also shapes the birth, life, and death of stars. That range isn't an exaggeration. The very process that makes your drink cool down operates on the same foundation as the processes that warm planets, brighten night skies, and fuel the engines of the universe. You can see entropy in motion with something as common as a cup of ice water. When you drop ice cubes into a warmer liquid, the coldness doesn't stay contained in neat blocks. The temperature difference drives tiny flows of energy between the warmer water and the colder ice. Molecules in the liquid bump against the rigid lattice of ice, transferring energy and gradually loosening its structure. It's easy to watch the ice cube shrink, but what's happening at a deeper level is that the system is shifting toward an arrangement with more possible microscopic states. A fully melted mixture offers far more configurations for its molecules than a clean separation between solid and liquid. The ice cube is a low entropy region of well-arranged molecules. The blended liquid is a higher entropy region where the molecules move freely. This change is not dramatic, it's simply natural. The transformation unfolds quietly because the system has access to more ways of being once the partitions dissolve. Even if you replace water and ice with two different liquids, say, a dark syrup and a clear one, you'll notice a similar drift. The separate layers don't remain stable unless something physically prevents them from mixing. Once they touch, the slight movements and collisions at their boundary encourage them to interweave. The separation represents a narrow collection of possibilities, while the mixture represents a broader range. The diffusion of one into the other isn't chaotic. It's a slow blending, guided by the preference of the system for states with more microstates available. Entropy affects substances even when you can't see the changes happening. Take a sealed container of gas. At first, you might imagine the gas molecules sitting still or distributed unevenly, but they are constantly in motion, bouncing around, colliding, exchanging tiny amounts of energy. If you divide the container into halves and allow the gas molecules to move freely, they will quickly spread into both sections. Nothing instructs them to do so. They simply follow the paths available to them. A uniform distribution is vastly more probable than an uneven one. That's entropy guiding the system toward a condition where the particles have more room and more combinations to occupy. This pattern carries over to heat, pressure, and concentration differences in any environment. If you warm one end of a metal rod, the heat flows toward the cooler end. Molecules or electrons carrying that energy don't coordinate with each other. They move and collide randomly, and the result of that randomness is the smooth spread of energy. The warm end cools, the cool end warms. Eventually the rod reaches a uniform temperature, and even though this process seems mundane, it is the same principle that dictates much larger flows of energy in the universe. Consider the air around you. Warm air rises because the molecules in it move faster, creating lower density and allowing cooler air to flow beneath it. The resulting circulation patterns produce breezes, weather changes, and sometimes entire storm systems. These movements aren't chaotic in the sense of being meaningless. They arise because temperature differences represent low entropy conditions. As heat spreads and energy equalizes, the system moves into a state with more accessible microstates. Weather evolves because the atmosphere is constantly shifting toward configurations that accommodate energy in more distributed ways. The same behavior appears in the cooling of a cup of coffee. As the coffee sits on a table, it loses heat to the surrounding air. The energy flow isn't dramatic, it's steady. Warm molecules near the surface transfer energy to cooler air, and this continues until the coffee matches room temperature. The process may seem trivial, but it is governed by the same principles that dictate how stars release energy into space. Both involve high-energy regions losing energy to surroundings that can absorb it. Both rely on the statistical tendency toward greater distribution. Both run in one broad direction, because the alternative is astronomically improbable. When you step into the natural world, you can find more examples. A lake warming under the sun experiences internal currents, because sunlight heats its surface while deeper layers remain cool. That imbalance creates movement as the water tries to distribute heat. Over time, the lake reaches a more uniform temperature. This doesn't mean every corner is exactly the same, but the general trend reflects the same principle. The system moves toward arrangements that require fewer constraints to maintain. Entropy doesn't force this, it simply describes the direction that is most accessible based on the number of available states. Mountains, rivers, and clouds show similar patterns. A snow-covered hillside doesn't melt evenly. Some areas warm faster due to sunlight or wind exposure, while others stay cold. Meltwater trickles downward following the easiest paths, gradually carving channels. Over long timescales, rivers shape landscapes because water seeks the routes with the least resistance. The precise details differ, but the underlying logic is tied to energy spreading and systems finding easier pathways. Over time, landscapes shift from sharp contrast to smoother ones, because the forces involved naturally move towards states with more freedom, more possible paths, and fewer rigid constraints. These ideas extend into the structure of planets themselves. Inside Earth, heat from its formation and radioactive decay moves outward. The center remains extremely hot, while the surface is much cooler. This gradient drives convection currents in the mantle, slowly moving solid rock in cycles. The movement shapes continents, volcanoes, and earthquakes. What appears as geologic activity is, at its core, the redistribution of energy following the same thermodynamic principles that cool a mug of tea. The scale is enormous, but the logic is the same. Entropy also plays a role in weather systems larger than simple breezes. Storms form when warm air meets cooler air. The contrast creates instability, and the atmosphere tries to spread energy more evenly. Storm clouds build as moisture rises and condenses. Thunderheads accumulate, winds accelerate, and rainfall spreads heat as water droplets release energy when they form. These shifts produce temporary structures, but the driving force behind them is the same gentle push toward balance. Over time, the storm expends its concentrated energy and gradually weakens. The atmosphere settles into a more distributed state. The entire process, wild as it looks, reflects the same principle working inside a melting ice cube. When you step beyond Earth and look toward space, entropy appears in every direction. Stars, for example, are engines built on thermodynamic imbalance. In their cores, nuclear fusion produces immense amounts of energy. That energy radiates outward, raising the entropy of the star and its surroundings. The star remains stable only as long as the outward pressure of energy balances the inward pull of gravity. Over time, as the star consumes its fuel, the balance changes. Eventually, the energy output declines, and the star collapses into new forms. Some become white dwarfs, others explode in supernovae, spreading heavy elements throughout space. The supernova stage, though violent, is another expression of entropy. Concentrated energy and matter are flung outward, giving the universe a huge number of possible new arrangements. The explosion is spectacular, but the driving force is the same natural redistribution that cools your drink. Even the cosmic microwave background, the faint afterglow left over from the early universe, is a product of entropy. In the early universe, everything was extremely hot, dense, and uniform. As it expanded, energy spread across increasing volumes of space. The temperature decreased, photons scattered less frequently. The universe shifted from a tightly constrained environment to one with far more possibilities. That shift is one of the clearest large-scale examples of entropy increasing. The faint radiation we detect today is the diluted remainder of that once concentrated energy. Its uniformity across the sky reflects how thoroughly energy has spread over billions of years. Entropy also shapes how galaxies move and evolve. In the early stages of the universe, matter wasn't evenly spread. Tiny fluctuations in density allowed gravity to pull material together, forming the seeds of galaxies. As galaxies formed, they heated their surroundings, released radiation, and converted gravitational potential into energy that helped increase entropy overall. Even though the matter became more concentrated in certain areas, the universe as a whole became more disordered because the formation of structure involved redistributing energy into more dispersed forms. This interplay between concentration and distribution is one of the central features of how entropy influences cosmic evolution. The rotation of galaxies also reflects entropy in subtle ways. When matter collapses under gravity, it doesn't fall inward perfectly. Slight variations in motion cause regions to spin. The formation of a rotating disk is a thermodynamically favourable outcome, because the system can occupy a huge number of states while still obeying conservation laws. The swirling patterns of stars and gas look organised on the surface, but the structure forms because it allows the system to follow paths with greater freedom. Over billions of years, galaxies collide, merge and reshape. Each interaction spreads energy further, producing new stars, new dust clouds and new arrangements. The larger structure continues to change because entropy provides direction for these transformations. If you consider how planets form, you can see another example of entropy guiding development. dust and gas orbiting a young star collide and clump together. While this might sound like increasing order, the collisions release heat and radiation, increasing the entropy of the environment. The eventual formation of a planet is not a decrease in entropy overall, it's a redistribution where the surroundings become more disordered, even as a stable structure emerges locally. Over time, planets cool, lose heat to space, and settle into balanced thermal states. The cooling process is familiar, similar to the cooling of any heated object. The planet radiates energy until its heat is more evenly spread across empty space. Once again, entropy shapes the evolution. Even black holes, some of the most extreme objects in the universe, have deep connections to entropy. When matter falls into a black hole, the number of accessible states associated with that matter increases dramatically. Black holes are known to have enormous entropy because the number of microstates that correspond to their mass and size is incredibly large. This concept surprised physicists when it was first proposed because black holes seem so simple. Featureless spheres defined by only a few properties. But behind that simplicity lies a vast number of possible microscopic arrangements. The horizon of black hole, the boundary beyond which nothing escapes, is associated with huge entropy because it encapsulates an enormous number of ways the contents within could be arranged. This means that even the most extreme objects in the cosmos follow the same statistical principles as a cooling drink or a drifting breeze. If you return from cosmic scales to everyday ones, the connection still holds. Your refrigerator works by moving heat from one place to another. It keeps food cold by expelling heat into the surrounding room. This creates a local decrease in entropy inside the refrigerator while increasing entropy in the environment. The overall trend remains consistent. Any process that concentrates energy or maintains low entropy regions requires external work. The machine must draw on electricity to maintain the difference in temperature. Without continuous input, the system relaxes back into balance. That relaxing motion, whether in a kitchen appliance or a star, follows the principle that the universe drifts toward the arrangements that offer the widest landscape of possibilities. Entropy even shows up in the behavior of living systems. Every cell in your body maintains order by consuming energy. The food you eat provides the fuel needed to keep molecules arranged in functional structures. Without that constant consumption, order would decay as the system followed the natural path toward equilibrium. But life uses energy to create and maintain complexity while releasing heat and waste into the environment. The net effect is always an increase in entropy. Growth, metabolism, and cellular repair all follow this pattern. Living organisms are pockets of low entropy that persist by increasing entropy elsewhere. This balance doesn't contradict thermodynamics, it depends on it. When you step back and consider these examples together, it becomes clear that entropy isn't isolated to rare or unusual events. It's woven into everything that changes, moves, warms, cools, mixes, spreads, or evolves. A melting ice cube and a dying star both follow the same universal tendency, scaled up or down depending on the system. Temperature, energy flow, diffusion, radiation, molecular motion. They all behave in ways that match the statistical drive toward more accessible states. This widespread presence of entropy doesn't make the universe feel chaotic. Instead, it brings a kind of clarity. Processes that might seem unrelated connect through a single underlying principle. Whether you're watching frost melt on a window or looking at images of distant galaxies, the same quiet logic is at work. The systems drift toward conditions that offer more pathways for their components. The details differ, molecules here, plasma there, but the overall direction is the same. Plenty of people hear the word chaos and imagine something unruly, unpredictable, or broken. Yet if you pause long enough to look closely at what appears chaotic, patterns begin to surface in ways that are surprisingly steady. Chaos isn't the absence of structure, it's the presence of countless small interactions that give rise to forms you can't fully predict moment by moment, but can still understand in broader terms. This is where entropy becomes especially interesting, because it doesn't simply guide systems toward disorder. It also shapes the subtle kinds of order that emerge within that disorder. The world isn't divided between tidy arrangements and meaningless scatter. Instead, most real systems sit somewhere in between, where messy interactions create their own forms of regularity. One example that often surprises people is the way turbulence forms in water. If you pour water smoothly from a jug, the flow might look calm at first, but once it speeds up or drops from a greater height, the liquid twists and curls into what looks like disorganized motion. These swirls are not identical from moment to moment, and you can't track each droplet precisely, yet the patterns they form are not random. They follow repeatable shapes, loops, and spirals that arise whenever water flows at certain speeds. These structures aren't imposed externally. They appear naturally because of how the molecules interact. Entropy encourages the system to explore many configurations, and within those configurations, certain shapes repeatedly emerge. What looks chaotic is actually a kind of patterned motion arising from interactions too numerous to track. That theme shows up in everyday weather as well. Wind gusts don't blow in straight lines. Clouds shift and fold. Storms form, strengthen, weaken, or drift in ways that seem unpredictable minute by minute. But zoom out, and the behavior becomes easier to describe. Weather systems follow broad-stroke patterns that repeat season after season. The atmosphere is filled with swirling structures, jet streams, pressure cells, rotating storms that form because the system is constantly trying to distribute heat more evenly. The small movements inside a storm may be chaotic, but the overall shape of the storm comes from consistent interactions between temperature, moisture, and pressure. The hidden order inside the chaos reflects the same thermodynamic tendencies that guide simpler systems, just scaled up to something enormous and dynamic. You can see versions of this hidden order in something as simple as cream mixing into coffee. It begins with distinct curls and streaks. The boundaries wiggle and stretch. Tiny eddies form at the edges where the liquids meet. Each swirl looks different, and the details shift every second. Still, the overall evolution follows a predictable path. First, distinct structures form, then they stretch. Finally, they fade into uniformity. The small-scale motion is sensitive to tiny differences, but the large-scale behavior arises reliably because the system is exploring its possible states. Entropy doesn't eliminate structure. It allows structures to appear as natural byproducts of many interacting parts. The same idea appears when you shake a box containing a mix of objects, say, nuts and bolts. At first glance, the mixture looks disordered. But if you keep shaking, the objects often separate into layers because items with certain shapes or sizes settle differently under vibration. This outcome isn't engineered. It appears spontaneously because of gravity, collisions, and the way objects fit together. Entropy encourages a large number of possible arrangements, but not all arrangements are equally stable. The ones that remain are often those that balance the forces involved. The results aren't perfectly ordered, but they're not purely random either. They inhabit a middle space where the system finds regularity within a messy environment. In biological systems, this hidden order is even more visible. Consider how cells maintain their internal environments. Inside a living cell, molecules bounce around, react, break apart, assemble, and drift. At a microscopic scale, it looks chaotic, but zoom out and you see reliable cycles. The cell produces energy, repairs itself, builds proteins, and exports waste. These cycles depend on countless small interactions that are individually unpredictable, yet collectively stable. The consistency of life is built on top of molecular chaos. Entropy drives particles to explore many states, and within that exploration, biological processes use energy to guide certain interactions into useful patterns. The overall structure repeats across trillions of cells, not because any one molecule follows a script, but because the system as a whole settles into patterns that emerge reliably. This mix of chaos and order also shows up in ecology. Forests, for example, don't grow in neat rows. Trees sprout in different places depending on sunlight, soil, rainfall, and seed distribution. Animals move unpredictably as they forage or migrate. Weather shifts their habitats. None of these factors remain constant. But even with all that unpredictability, ecosystems develop stable structures. Predator and prey populations rise and fall in cycles. Plant species distribute themselves in ways that reflect available resources. Rivers carve channels that redirect growth patterns. The apparent messiness is filled with regularities that emerge over long times. Entropy pushes systems towards states that don't require precise coordination, and out of that, freedom comes stability at large scales. The interplay between chaos and underlying order becomes especially clear when you consider fractals, structures where a pattern repeats itself at different scales. Fern leaves, branching trees, river networks, coastlines, lightning bolts, and even certain kinds of chemical reactions show fractal-like patterns. These patterns look complicated, but they arise naturally from simple rules applied many times. The details are chaotic. No two branches or waves are exactly alike, but the overall form is consistent. Entropy allows microscopic variations while permitting a recognizable macroscopic structure. Nature doesn't need perfect precision to build repeating patterns. It only needs general tendencies that hold across many scales. Entropy can create order through processes like self-organization. This happens when systems with many interacting parts spontaneously form structured patterns without any external guidance. A well-known example is how convection cells form in a heated liquid. If you warm the bottom of a fluid enough, the heated portion rises while cooler liquid sinks. The exchange creates rolling, repeating shapes that fill the container. Before the heating begins, the liquid appears uniform. As energy flows through it, structured motion emerges. When the energy input stops, the pattern disappears, and the system returns to equilibrium. The shape wasn't imposed from outside. It was an expression of how the system used incoming energy to settle into a dynamic structure that allowed heat to distribute efficiently. You can find a related phenomenon in sand dunes. Sand grains move chaotically when wind blows across them. Any individual grain may bounce, roll, or lift unpredictably. But when you step back, dunes form recognizable shapes. Some develop gentle slopes. Others build steep faces. Their forms depend on wind direction, sand supply, and terrain. Even though the movement of individual grains is random, the collective behavior produces consistent patterns because certain shapes allow the sand to shift more easily. The dunes don't stay the same forever, but their general structures persist because the system settles into configurations that balance energy input and the ease of movement. Entropy plays a role in these structures by ensuring that systems with many moving parts explore wide ranges of configurations. In that exploration, certain pathways require less energy, or align better with the forces at play. The system doesn't choose these pathways consciously. It simply falls into them because they represent outcomes that accommodate disorder while allowing flow. As long as energy continues entering the system, these patterns persist. When the external input stops, the system relaxes back into a simpler, more disordered state. This is why dynamic order often disappears when the driving force fades. If you turn to chemical reactions, you'll find more examples of hidden order. Certain reactions produce oscillating patterns, where concentrations of chemicals rise and fall periodically. These reactions involve feedback loops that cause repeating changes in colour or composition. To someone watching for the first time, the mixture looks like it's pulsing with its own rhythm. But the underlying mechanics involve countless small interactions between molecules. The order arises because the reaction network supports cycles that allow energy and matter to pass through specific pathways. Entropy continues to increase overall, but the system's internal structure becomes temporarily ordered because energy flows through it in a specific manner. The same principle helps explain why crystals can grow out of seemingly chaotic environments. In a solution filled with drifting molecules, nothing looks structured. But when conditions are right, temperature, concentration, solvent properties, molecules attach to one another in repeating patterns. Single molecules don't plan where to go. They bump into surfaces, attach when the fit is compatible, and detach when it's not. Over time, a stable structure forms because it provides a low-energy way of arranging molecules under those conditions. The growing crystal doesn't represent a violation of entropy. It forms while the surroundings release energy, increasing entropy elsewhere. This relationship between energy flow and temporary order becomes even clearer when you consider living organisms. A single cell organizes itself through thousands of chemical pathways happening simultaneously. While the internal environment might appear crowded and chaotic, the cell maintains structures like membranes, DNA strands, organelles, and protein complexes. These structures persist because the cell imports energy through nutrients or sunlight, using that energy to reduce internal entropy. Outwardly, the system increases entropy by releasing heat and waste. Order inside arises because the cell continuously channels energy in specific directions, and that flow supports complexity. Without that energy, the cell's internal structure collapses. Entropy wins, not because order is forbidden, but because maintaining order requires work. This same balance appears in multicellular life. Organisms maintain homeostasis by constantly adjusting temperature, nutrient levels, and chemical composition. Beneath the surface, countless processes behave chaotically, yet the overall structure persists. Entropy drives systems toward disorder, but living organisms continually invest energy to hold onto patterns that support life. This investment doesn't break thermodynamic rules, it operates within them. Complexity flourishes because the system uses energy to carve out islands of order within a wider landscape of disordered possibilities. Chaos and order intersect in the natural world in ways that often go unnoticed. Consider the shapes of clouds. They might look random, but they form recognizable types: cumulus, cirrus, stratus, based on humidity, temperature, and wind. Within each cloud, droplets move unpredictably, but the cloud as a whole follows stable patterns because the atmosphere directs moisture into forms that reflect broader conditions. Entropy ensures that heat and energy spread, while the physical properties of air guide the shapes that form during that spread. You can find a similar interaction in the growth of plants. Leaves sprout in patterns that maximize sunlight exposure. Branches divide at angles that improve stability and nutrient distribution. These arrangements emerge because the plant responds to energy flows, chemical gradients, and environmental pressures. The molecular interactions inside each cell are chaotic, yet the plant develops predictable shapes. Entropy drives the underlying processes, while biological rules channel them into structured growth. Another place where this interplay becomes clear is in traffic patterns. Individual drivers react to lights, signs, and each other in countless small ways that can't be perfectly predicted. Yet when many cars travel on the same road, large-scale patterns emerge. Congestion forms at certain points. Flow becomes smoother in others. Peaks and valleys in traffic speed appear repeatedly depending on time of day and road design. Drivers behave unpredictably on the small scale, but the entire system displays patterns. This reflects how many chaotic interactions can still produce broader regularities when they follow shared tendencies. The hidden order also shows up in economics, communication networks, and social dynamics. Small decisions cascade into larger trends. Individuals make unpredictable choices, but communities develop consistent behaviors. Price changes ripple through markets, ideas spread through populations, new technologies shape interactions. None of these outcomes are centrally coordinated. They appear because systems with many interacting agents settle into patterns that reflect both randomness and underlying constraints. Entropy allows freedom of motion. Structures arise because certain arrangements persist more easily. In all these examples, the coexistence of chaos and order doesn't contradict the idea that entropy increases. Instead, entropy provides the foundation for understanding why patterns arise in the first place. When a system has many possible states, some states are more accessible or more stable than others. Even chaotic interactions tend to settle into regions of possibility that match the underlying physics, energy conditions, or environmental pressures. Hidden order isn't something imposed on chaos. It emerges from the way systems behave when they explore their available configurations. Understanding this interplay can make the world feel a little less intimidating. Chaos doesn't mean things are out of control. It often means that countless small interactions are shaping something stable in ways that aren't immediately visible. Entropy doesn't erase order. It filters possibilities. Patterns appear because certain pathways require less effort than others. Most people don't realize that the everyday frustration of a room steadily drifting into clutter has the same scientific roots as melting ice, cooling stars, and mixing liquids. A messy bedroom might seem like something caused purely by habits, schedules, or a lack of cleaning time, but even beneath those surface explanations lies a deeper principle shaping the outcome. If you look at the situation from the standpoint of entropy, the slow spread of clothes, papers, mugs, books, chargers, and everything else that finds its way onto shelves and furniture stops feeling like a personal flaw and starts looking like a natural result of how systems behave when many small interactions occur with little effort required to maintain structure. Think about the act of entering a room. Just opening the door lets in a small burst of air. That slight movement may shift a paper, tilt a cushion, or nudge a lightweight object a fraction of an inch. You rarely notice those tiny changes, but they accumulate. If you carry something with you, shoes, a bag, headphones, those items end up somewhere, and unless you deliberately choose the most structured possible location for each one, they drift into more probable places. A dresser with many closed drawers requires effort to open. A chair or nightstand requires none. The easier route almost always wins. These little decisions reflect the same principle that explains why molecules mix, why heat spreads, and why systems move from narrow sets of possibilities into broader ones. When you step out of your room again, you leave behind evidence of your presence. A blanket shifts slightly. A book sits in a position that gives easier access than placing it back onto the precise spot on a shelf. A pillow isn't fluffed the same way it was in the morning. These small actions don't feel like choices. They feel like the natural way objects move through your hands. But from an entropy perspective, each of these movements broadens the range of possible microstates the room can inhabit. A tightly organized space represents a limited region of possibility. A loosely arranged space occupies an enormous one. Without constant effort pulling the room back into that limited region, it naturally drifts into the broader region. This drift is not chaotic, it's just more probable. To see why, imagine a drawer filled with neatly folded shirts. There are only a handful of configurations where every piece is arranged perfectly. A slight disruption, pulling out one shirt, returning another, creates many more possible arrangements that fall under the category of slightly messy. The second law of thermodynamics would describe the neat drawer as a low entropy state, not because it's morally superior or preferable, but because it represents a very small number of possible arrangements of molecules. A rumpled drawer contains vastly more possible arrangements, and therefore is simply more likely to occur. Unless energy is consistently added to the system, in this case your effort, the room won't return to the organized state on its own. This same logic applies to surfaces in the room. A desk might start the week clear, but as you interact with objects, placing a pen down, leaving a receipt from a store, setting a glass aside, opening a notebook, you create small traces of your activity. The likelihood that all those objects will independently return to their original locations without deliberate effort is effectively zero. Even if you move through the room mindfully, the number of ways items can be slightly off is so much larger than the single arrangement in which everything rests perfectly aligned. Over time, the system settles into one of those higher entropy states because they require no maintenance. Laundry contributes heavily to this process as well. Clothing changes state constantly throughout the day, from worn to discarded to washed to folded. Each transition gives the system countless opportunities to enter a configuration that isn't the one you intend. A shirt draped over a chair instead of being placed in a hamper, or a pair of socks left near the foot of a bed, isn't the result of the universe sabotaging cleanliness. It's simply the natural outcome of a system with many possible states. Placing clothes exactly where they belong requires more energy than letting them fall into the general region where they were removed. You can even see the same principle in how items accumulate in rooms over time. Every new object you acquire enters the system with its own set of potential locations. Unless you deliberately assign it a place and consistently return it there, it tends to drift into the areas you use most often. The path of least resistance draws items into the most accessible spots, creating subtle clusters. These clusters don't form out of chaos. They form because there are more ways for things to be slightly out of place than precisely aligned. Entropy also plays a role in how dust collects. Dust particles move with air currents caused by motion, temperature differences, and even slight changes in pressure when you enter or exit the room. They settle on surfaces where the air slows down. A perfectly dust-free room represents an extremely low entropy arrangement, because dust particles must all avoid landing in countless places. A thin layer of dust is far more probable. Even if you clean thoroughly, dust begins accumulating again almost immediately. It settles because there is no natural mechanism keeping it suspended indefinitely. Without constant intervention, dust spreading over surfaces is the default outcome. The distribution of objects in a room also changes because you interact with certain places more than others. Nightstands, desks, chairs, and the area near the foot of a bed see more activity than corners or high shelves. These interactions create small disturbances. Movement in one part of the room redistributes items in subtle ways, while areas you rarely touch remain orderly because they experience fewer interactions. In thermodynamic terms, these high interaction zones have more exchanges of energy and matter, giving them more chances to enter states with greater entropy. Low interaction zones stay tidy longer because they have fewer opportunities to drift. Even the way furniture is arranged contributes to the tendency toward messiness. Open shelves invite objects to be placed on them. Flat surfaces with no obstacles make excellent landing spots for whatever you're carrying. Closed storage, on the other hand, requires deliberate steps. Opening a cabinet, placing an item inside, closing it again. A room filled with accessible surfaces encourages entropy to manifest more visibly. Everything that can accumulate eventually does. This doesn't indicate neglect, it reflects how systems behave when low-effort paths dominate. The same idea extends to paperwork, books, and electronics. A single piece of paper on a desk has only a handful of possible neat positions. Once you place a second sheet down without aligning it, the number of possible configurations increases dramatically. Add a few more sheets and the number grows even larger. A pile that looks messy is simply occupying one of the many available arrangements that require little effort to reach. The neat arrangement requires all pieces to align precisely, which the system has almost no chance of producing spontaneously. Electronic devices follow similar patterns. Cords coil, twist, and drape because the number of tangled configurations dwarfs the number of neatly arranged ones. Without conscious effort, tangled becomes the default state. Entropy also affects how you perceive the mess. When a room becomes cluttered, your brain picks up on the irregularity because humans tend to notice deviations from patterns. A tidy room has clear lines, visible surfaces, and predictable placement of objects. A cluttered room has broken lines, irregular forms, and scattered items. Your mind interprets this as disorder because it deviates from the small set of neat configurations you're accustomed to seeing. But from the standpoint of physics, the cluttered state is more probable, not more chaotic in the sense of being uncontrollable. It simply represents a state the system can reach with minimal intervention. Even cleaning follows the logic of entropy. Tidying a room means investing energy to move the system from a highly probable state to a far less probable one. This is why cleaning feels like work. You're reversing a natural drift, pushing the system back into a constrained region. The second law doesn't forbid that. Entropy can decrease locally if work is put in. But without continued effort, the room slides back toward the higher entropy region automatically. It doesn't do this suddenly or dramatically. It happens through countless small motions, decisions, and interactions. One of the more subtle contributors to a messy room is human behavior under limited time or attention. When you're focused on something else, studying, relaxing, getting ready for the day, you naturally take the easiest path for object placement. This behavior mirrors thermodynamics. Systems tend to follow the easiest routes. If putting something away requires multiple steps, while placing it on a nearby surface requires one, the one-step option usually wins. Over time, the room reflects that accumulation of low-effort choices. This isn't laziness, it's efficiency. Your brain optimizes energy use without consciously thinking about entropy, yet the result aligns perfectly with the tendencies entropy describes. Another influence is variation in daily routines. On one day, you might use one set of items. On another day, different objects come into play. Each routine introduces a distinct pattern of interaction. Because these patterns vary, objects end up in slightly different places each time. The shifting distribution of items creates a broad range of configurations, all of which belong to the high entropy region. A tidy room requires uniform routines or constant resetting. Most people naturally drift away from those constraints, so the room reflects the diversity of your activities. Room temperature can even play a small role. Warm air rises and cool air falls, creating microcurrents that influence the movement of lightweight objects. These shifts don't dramatically rearrange a room, but they contribute to the gradual randomization of small items. Curtains sway, papers shift, and dust dances. All of these motions increase the number of states the room explores. Once again, entropy expands the range of possible configurations. Pets, if you have them, accelerate the process. A cat jumping onto a shelf or a dog brushing against a blanket introduces random movements that push the room into new states. Animals don't intentionally create disorder, but their interactions add to the number of possible configurations. Every nudge or movement contributes to the gradual shift toward higher entropy. This mirrors the way molecules interact in physical systems. Small collisions and movements create large-scale effects over time. Even the way light enters a room can influence its entropy. Sunlight warms surfaces unevenly, creating thermal gradients that can drive tiny air movements. Shadows shift throughout the day. Objects expand and contract slightly with temperature changes. These effects are subtle, but over long periods, they contribute to small motions that expand the number of states the room can inhabit. It's another reminder that even gentle environmental influences follow the same principles that guide thermodynamic systems on every scale. Understanding all of this doesn't magically prevent a room from getting messy, but it reframes why it happens. A cluttered room isn't evidence of failure, it's a textbook illustration of entropy. Without constant input of energy, your effort, the system moves toward a state with more possibilities. That movement is natural. It's the same movement behind diffusion, cooling, and cosmic evolution. The scale is smaller, but the logic is identical. Recognizing this can also make tidying feel less burdensome. Instead of seeing a messy room as something that shouldn't exist, you can view it as a natural state that emerges from the way you interact with your environment. Cleaning becomes the act of adding energy to create an uncommon arrangement. Maintaining it means continually resisting the system's statistical tendencies. There's no mystery as to why it requires so much effort. You're pushing against the default. It can be surprising to realize that the history of the entire universe can be traced through the gradual increase of entropy. People often think of the cosmos in terms of spectacular events: exploding stars, swirling galaxies, expanding space. But beneath those dramatic scenes lies a quiet and persistent trend. From the earliest moments after the Big Bang all the way to the present, the direction of change has been guided by the same principles that govern small, everyday processes. When a cup of tea cools, when ice melts, when air diffuses, those are tiny echoes of the broader cosmic narrative. Understanding that story doesn't require imagining anything mystical or abstract. It simply requires following how energy spreads, how matter rearranges itself, and how the overall number of possible states available to the universe keeps growing. To picture where this began, imagine the universe in its earlier stages. Right after the Big Bang, everything was compressed into an unimaginably dense and hot state. There were no stars, no planets, no atoms, not even space as we know it. The entire cosmos was a uniform sea of energy and elementary particles. That initial state might sound chaotic, but in a thermodynamic sense it was actually low in entropy. The reason is that despite the extreme temperature, the distribution of matter and energy was uniform. Rules governing gravity hadn't yet created significant differences from place to place. A uniform state represents fewer distinct microstates than a universe filled with complex structures. As space expanded and cooled, entropy began rising because the universe suddenly had room to explore more possible arrangements. As the expansion continued, small fluctuations in density allowed gravity to take hold. Regions that were slightly denser pulled in more material, forming the seeds of galaxies. These fluctuations weren't imposed intentionally. They were tiny quantum variations that expanded with space. Once they appeared, the universe found itself able to occupy an enormous range of new configurations. Matter could gather, clump, heat up through gravitational collapse, and form stars. Those stars would fuse elements, radiate light, and enrich their surroundings with energy. Each of these processes increased entropy overall, even though they produced pockets of structure along the way. Stars themselves are powerful drivers of entropy. Inside their cores, hydrogen fuses into helium through nuclear reactions that release tremendous amounts of energy. That energy escapes into space as light and heat, spreading out in all directions. When the energy accumulates at the star's core, the star remains stable because gravity and outward pressure balance. But every photon that escapes contributes to increasing the number of possible microstates in the surrounding environment. The star becomes a source of entropy, radiating energy outward for millions or billions of years, while the star itself is a structured object. The overall entropy of the universe rises steadily because of how that structure influences the distribution of energy. As stars evolve, their final stages continue this trend. Smaller stars cool and shrink into white dwarfs, radiating energy over long periods. Larger stars explode in dramatic events called supernovae. These explosions eject huge amounts of matter and energy into space. The energy disperses rapidly, heating surrounding gas and creating shockwaves that trigger the formation of new stars. The dispersed material includes heavy elements that later become the building blocks of planets, mountains, oceans, and even living organisms. From an entropy standpoint, these explosions represent enormous increases in the number of possible states the universe can explore. The structured core of a massive star transforms into scattered atoms and photons. The resulting debris cloud has vastly more ways to exist than the concentrated matter it came from. The story continues as galaxies form. Galaxies are not random assemblies of stars. They arrange themselves into spirals, ellipses, and irregular shapes depending on their interactions and histories. Yet despite their structure, galaxies represent a step toward higher entropy because they form through gravitational collapse, which heats surrounding areas, releases radiation, and leads to ongoing star formation. Every star formed within a galaxy becomes another entropy-producing engine, radiating energy into space. The rotation of galaxies, the collisions between them, and the merging of structures all contribute to further spreading energy and matter. Over time, these interactions create even more complexity. Galaxy clusters form, bound together by gravity. These clusters contain hot gas and dark matter, with temperatures that can reach millions of degrees. The hot gas emits X-rays, losing energy that spreads across vast distances. Even though the clusters remain gravitationally bound, the energy flow within them contributes to increasing entropy. The underlying story remains consistent. Structures emerge, energy flows, and the cosmos gradually moves into states with more possible ways to arrange its components. The cosmic microwave background, the faint glow that fills the universe, is another important piece of this story. It represents residual radiation from the early universe, when electrons and protons first combined to form atoms. Before that moment, light couldn't travel freely because particles collided constantly. When atoms formed, the universe became transparent, allowing light to escape. That light has been travelling ever since, stretching into longer wavelengths as the universe expands. The uniformity of this radiation reflects how thoroughly energy has spread across the cosmos. What we observe today is a nearly even glow, interrupted only by tiny variations that reveal subtle differences in early matter distribution. These variations eventually gave rise to galaxies and larger structures. The background radiation shows how the early universe moved from a low-entropy uniform state into a more complex and distributed one. Even the expansion of space itself plays a role in the cosmic entropy story. As space expands, the volume available to radiation increases. This expansion allows energy to spread out further, contributing to the overall rise in entropy. The universe becomes cooler and more sparse as time goes on, but this cooling doesn't mean entropy is decreasing. It continues to increase because the number of accessible states grows as space expands. More room equals more possibilities. More possibilities equal higher entropy. Planets and moons form from the debris of star systems. The process begins with clouds of dust and gas pulled together by gravity. As clumps grow, they collide, merge, and accumulate material. Each collision generates heat that radiates away. Even though the result is a solid planetary body, the formation involves significant increases in entropy. The heat radiated into space carries energy that becomes part of a much larger pool of possible configurations. Over time, planets cool, releasing more heat into their surroundings. Internal processes like volcanic activity, tectonic movement, and magnetic field generation all rely on energy spreading from concentrated sources. These processes shape the surface of the planet while contributing to the universe's overall tendency toward higher entropy. Life emerges in this context not as an exception to entropy, but as part of the story. Living organisms maintain internal structure by consuming energy from the environment. Plants gather sunlight, animals eat plants or other animals, and microbes break down organic matter. Every step in these processes increases the entropy of the larger system. Life isn't a violation of the second law. It's a demonstration of how local decreases in entropy can occur when energy flows through a system. The broader surroundings always experience a net increase. The rise of life added another layer of complexity to the cosmic story, but within the same thermodynamic framework. Civilizations, technology, and human activity continue the trend. Every machine, every engine, every electronic device operates by converting energy into less organized forms, mainly heat. Whether it's a car accelerating, a laptop processing information, or a stove heating a pan, each action increases entropy. Human societies produce complex structures and systems, but they rely on flows of energy from food, fuel, sunlight, and other sources. These flows maintain local order while contributing to the universe's overall shift toward more dispersed energy. Zoom out again, and the cosmic timeline becomes a continuous sequence of increasing entropy. The early universe was hot and uniform. Over time, matter clumped into galaxies, stars, and planets. These structures radiated energy into the vastness of space. Stars aged, exploded, or collapsed. New stars formed. Planets cooled. Life arose. Energy continued spreading. Every transformation moved the universe toward more varied configurations, even when the formation of structure created localized order. The long-term future of the universe is still guided by entropy. Stars will eventually exhaust their fuel. Smaller stars will cool into black dwarfs. Larger stars may collapse into neutron stars or black holes. Galaxies will drift apart as space expands. Black holes will slowly evaporate through a process known as Hawking radiation, releasing tiny amounts of energy over immense timescales. The energy released will spread across a universe that becomes colder and more diffuse. This isn't a sudden end. It's a gradual transition toward a state where energy is evenly distributed, and no large-scale processes remain to produce new structures. Even in that distant state, the number of possible microscopic arrangements will be enormous. Entropy will be extremely high. This long-term trajectory isn't something to fear. It reflects the same natural tendencies that govern everything from heat flow in everyday objects to the evolution of galaxies. Rising entropy doesn't mean everything is falling apart. It means that energy and matter continue exploring the expanding landscape of possible arrangements. Structure emerges when conditions allow, and dissolves when the energy that sustains it dissipates. The universe grows in complexity, and then gradually relaxes. All of it follows the same statistical direction. Studying cosmic entropy can change how you see the night sky. The light from stars is the result of energy flowing outward, increasing entropy in the space around them. The formation of planets from dust clouds reflects entropy-driven processes. The gentle glow of distant galaxies is a snapshot of energy spreading across space. Even the faint cosmic microwave background is a memory of entropy increasing in the early universe. The entire sky becomes a record of how energy has moved and continues to move. This understanding can also reshape how you view the role of order in the universe. Order isn't the default. It's the result of temporary conditions where energy and matter become concentrated enough to form patterns. These patterns don't violate entropy. They exist because energy flows through systems, creating local decreases that enable structure. Once the energy flow stops, the structure fades, stars burn out, mountains erode, living organisms pass away, technological artifacts degrade. The cosmos continually transitions through states where order appears, dissolves, and reappears in new forms. Recognizing the cosmic story written in rising entropy doesn't make the universe feel bleak. Instead, it reveals a steady, natural rhythm. Things form because energy is available to create and maintain them. They dissolve because energy spreads outward. That relationship between formation and decay is not a fight against inevitability. It's the pattern through which the universe evolves. It helps to step back from the grand scale of the universe and look more closely at the simple forces responsible for so much of what we see. Heat and energy may sound like basic topics, but they quietly shape events from the smallest interactions to the largest cosmic movements. You don't need complicated equations to appreciate their influence. Just noticing how temperature changes, how warmth spreads, and how energy moves is enough to understand why entropy matters. The paths these quantities follow are not random. They arise from clear tendencies that appear again and again, guiding systems towards states where energy is more evenly shared. Start with something familiar, a warm object placed in a cooler environment. Take a mug of hot water. The moment it sits on a countertop, energy begins transferring into the surrounding air. Molecules in the water jostle rapidly, passing some of that motion to nearby air molecules when they collide. Those air molecules then bump into others, carrying the added energy outward. Nothing in this process moves backward. The energy doesn't spontaneously regroup to make the mug hotter. It spreads. This spread reflects the heart of entropy. A concentrated store of energy represents a narrow set of possibilities. Once that energy disperses, the number of possible arrangements grows. You can see the same tendency if you compare areas in a room with different temperatures. If you heat one corner of the room, the warmth travels outward until the temperature becomes more uniform. This balancing act doesn't require deliberate guidance. Temperature differences create conditions where energy flows from higher concentration to lower concentration. That direction isn't forced, it's simply the direction with overwhelmingly more possible outcomes. When the room finally reaches a steady temperature, the system has settled into a state where the molecules can occupy a vast range of arrangements without producing noticeable differences. Even the way your own body deals with heat reflects this principle. When you exercise, your muscles generate heat. Without cooling mechanisms, your temperature would rise quickly. But your skin radiates heat outward, your sweat evaporates, and your bloodstream distributes warmth through your body. These processes keep you from overheating by moving energy away from concentrated areas. If they stop working, heat accumulates, and the uniformity breaks down. Maintaining a stable body temperature requires constant adjustments because energy always seeks to spread. Entropy shapes these biological processes by creating a direction for energy flow that your body must constantly counterbalance. Cooking offers clear examples as well. Place a piece of cold food in a hot pan, and heat moves from the pan into the food. The food becomes warmer as its molecules gain energy. Meanwhile, the pan cools slightly unless it continues receiving heat from a stove. This transfer of energy is what allows food to cook uniformly. Without heat flow, cooking wouldn't occur. And the reason heat flows at all is because concentrated energy does not remain stable when surrounded by areas that can absorb it. Entropy describes this redistribution not as a rule imposed on the system, but as the natural outcome of how many ways molecular energy can be shared. Electricity follows a similar pattern, though in a different form. When electrons move through a wire, they carry energy with them. Resistance in the wire leads to some of that energy converting into heat. The energy never disappears. It changes form, shifting from organized motion of electrons to disorganized vibrational motion of the atoms in the wire. This conversion increases the number of possible microstates because the energy is now distributed among many more particles. Even devices designed for efficiency cannot avoid this effect. Energy transfer always involves some spreading, because perfect preservation of structure would require conditions that are nearly impossible to achieve. A refrigerator provides another clear demonstration of entropy's influence. Inside the appliance, a compressor pumps heat out of the interior and releases it into the kitchen. The cold interior might appear to contradict the trend toward higher entropy, but the machine works by investing energy to remove heat. The surrounding room becomes warmer, increasing entropy overall. The cold compartment is a pocket of low entropy maintained by constant work. If the refrigerator loses power, it quickly drifts back toward equilibrium because heat naturally moves into regions that contain less energy. Once again, concentrated energy does not sustain itself without external effort. To understand why heat spreads the way it does, consider how energy is stored inside matter. At a microscopic level, heat is the motion of particles. Higher temperatures mean faster movement. These particles collide constantly. When a fast-moving particle strikes a slower one, the slower one speeds up, and the faster one slows slightly. These exchanges distribute energy across the system. Over time, repeated collisions lead to a uniform distribution of energy, not because particles seek balance, but because random collisions make evenly distributed states vastly more probable than uneven ones. The system cannot avoid this outcome without intervention. The same logic applies to gases. If you open a container of gas into a larger space, the molecules spread until they occupy the entire volume. The initial state, gas confined to one side, is a low entropy arrangement. The dispersed state allows for many more possible positions and velocities. Even if the gas were to momentarily cluster in one region due to random fluctuations, it wouldn't stay there. Subsequent collisions would push it outward again. Entropy describes this behavior quantitatively, but the idea is intuitive. More possible ways to exist equals a more likely state. Now consider what happens when light carries energy from one place to another. When light leaves a star, it moves outward through space, spreading its energy across growing distances. Each photon occupies a larger region as time goes on. The spreading of light increases entropy because the energy becomes less concentrated. The star itself also becomes more disordered over time because the energy that once stabilized it escapes. This doesn't make the star unstable all at once, but over millions or billions of years, the energy loss affects its evolution. Heat, radiation, and matter all follow similar tendencies because their behavior arises from probabilities. Even sound demonstrates how energy spreads. A loud noise carries energy through the air in the form of pressure waves. As those waves move outward, they weaken because the energy spreads over a larger area. Eventually, the sound fades into the background of the environment. The process isn't reversible. Sound won't spontaneously focus itself back into a loud source. It spreads until it becomes indistinguishable from ambient motion. This spreading represents an increase in entropy, as the organized pressure variations turn into tiny vibrations distributed throughout the air. On larger scales, heat and energy flow through natural systems in ways that mirror these smaller examples. Oceans, for instance, circulate heat across the planet. Warm water near the equator moves toward cooler regions, while cold water sinks and travels toward warmer zones. These circulation patterns help regulate climate. Without them, temperature differences across the planet would be far more extreme. The ocean's constant motion reflects the same principle that makes a hot object cool. The system tends toward distributing energy more evenly because concentrated heat in one region represents a smaller number of possible configurations. The atmosphere behaves similarly. Sunlight warms the Earth unevenly, creating temperature imbalances. Those imbalances drive winds, storms, and weather patterns. The atmosphere works tirelessly to redistribute heat, moving warm air toward cooler regions. This redistribution creates complex structures, but the underlying direction is simple. Energy moves from areas of surplus to areas of deficit. Weather appears chaotic because it involves countless interacting variables, but the general trend follows the spread of heat. Entropy grows as the atmosphere explores more configurations, even while temporary structures like storms form and dissipate. Inside the Earth, energy flows from the hot core outward. Radioactive decay produces heat that travels through the mantle. The movement of molten rock, convection currents, and tectonic shifts all arise from these flows of energy. Earthquakes, volcanoes, and the drift of continents all stem from the redistribution of heat. The driving forces are slow, but they follow predictable tendencies. Concentrated heat deep within the Earth pushes upward, spreading into cooler layers. This movement reshapes the planet over geological timescales, not through sudden leaps but through the steady influence of entropy. Entropy plays a central role in stars as well. In the core of a star, nuclear fusion releases enormous amounts of energy. That energy pushes outward, balancing gravity. As it escapes into space, the star's entropy increases. The radiation spreads across vast distances, contributing to the growing disorder of the universe. When a star eventually exhausts its fuel, its structure changes. Some swell into red giants, others collapse into white dwarfs or neutron stars. The transitions reflect how the internal energy of the star becomes redistributed. The collapse of a star might seem like increasing order, but the release of gravitational energy into heat, light, and particles increases entropy overall. In the realm of living systems, heat and energy shape biological processes in subtle but essential ways. Every chemical reaction inside your body involves energy transfer. Some reactions release heat, others require it. Enzymes help guide reactions along favourable paths, but the underlying thermodynamic tendencies remain. A cell must import energy to maintain its structure. It cannot remain organized without continuous chemical processes that counteract entropy. Each time the cell uses energy, it contributes to the spread of heat into the surrounding environment. The balance between internal order and external disorder keeps the cell functioning. When organisms interact with their environment, the flow of energy becomes even more pronounced. Plants capture sunlight and convert it into chemical energy. Animals consume that energy and eventually release it as heat. Entire ecosystems operate on these energy flows. Heat and entropy shape food webs, population dynamics, and life cycles. Even though ecosystems display complexity, their functioning depends on the increasing disorder of the larger system. Energy moves through living networks before dissipating into the environment. The spread of energy is the foundation upon which biological organization rests. Human technology relies on these principles too. Engines, computers, lights, and machines all function by using energy and increasing entropy. A car engine burns fuel, producing motion and heat. The motion is directed, but the heat spreads into the environment. A computer turns electrical energy into calculations, but also releases heat that must be dissipated. A light bulb converts electricity into light and heat, with the heat representing energy distributed into many microstates. No device can avoid this tendency entirely. Even incredibly efficient machines increase entropy, because no process can convert energy perfectly without losses. This broad picture, heat spreading, energy diffusing, systems settling, might seem repetitive at first, but it's the core reason why entropy matters. Everything that happens depends on how energy moves. The shape of a hurricane, the glow of a star, the cooling of your dinner, the functioning of your heart, and the formation of galaxies all follow the same basic tendencies. Energy does not stay put when it can spread. Concentrated pockets of heat, matter or motion always tend towards states where they are more evenly distributed. The universe is built upon this steady flow. This understanding adds clarity to the earlier ideas about entropy increasing. Rising entropy isn't a decline in quality. It's a reflection of how energy naturally explores the most accessible arrangement. The spread of heat doesn't degrade the system in a moral sense. It simply reflects the natural progression of events. Complex structures arise along the way, but they rely on flows of energy that ultimately lead to more dispersed states. It's easy to think of entropy as something that belongs to physics labs, distant stars, or large natural systems, but one of the most important places it operates is inside your own body. Every thought you form, every movement you make, every breath you take, and every moment you spend resting is shaped by constant flows of energy. These flows create order in some places while increasing disorder in others, and the balance between those two directions forms the rhythm of your daily life. You don't have to sense molecules or track microscopic changes for these processes to matter. They are built into everything your body does to stay alive. Consider the simple act of waking up. When you open your eyes, your body has already been working for hours. Cells have continued their internal reactions, your heart has kept beating, and your nerves have maintained enough activity to keep essential processes going. All this requires energy, and every bit of that energy originates from food or stored reserves. The chemical bonds in the food you eat represent concentrated pockets of energy. When your body breaks them down, it redistributes that energy throughout your system. Some of the energy becomes heat, some powers cellular reactions, some supports movement. The spreading of that energy into forms that are eventually lost as heat is part of what drives entropy upward. Even while you're asleep, entropy is rising around you because your body is using energy to maintain order inside your cells. When you first stand up in the morning, the feeling of warmth that spreads through your muscles as they begin to move is another example of entropy at work. Your muscles convert stored chemical energy into motion by breaking down molecules like glucose or fatty acids. These reactions release heat, which then spreads through the surrounding tissues and eventually radiates outward from your skin. The heat does not gather in one place. It moves and dissipates because that distribution is more probable than confinement. Even the simple warmth you feel in your hands after holding a mug of tea forms because heat flows from the hotter object to the cooler one, equalizing temperatures and increasing the number of possible microstates that energy can occupy. Breathing is another process deeply connected to entropy. Every inhale brings in oxygen, which your cells use to break down nutrients. These reactions produce carbon dioxide as a waste product. The reason your body must push carbon dioxide outward is that keeping it confined inside your tissues would decrease the number of possible states the system can occupy. Letting it diffuse outward increases entropy. When you exhale, those molecules scatter into the air around you. They will never rearrange themselves back into your lungs on their own. They move from areas of higher concentration to lower concentration, following the same thermodynamic tendencies that guide the mixing of gases in a room. Your digestive system also demonstrates the importance of entropy. Food enters as structured material. Your body breaks it down into simpler components. Enzymes cut apart large molecules, and once they are separated into smaller pieces, they can travel freely through the bloodstream. This breakdown of structure releases energy and increases the number of possible ways those smaller molecules can be arranged. Some of the energy from digestion is captured and used to build or maintain structures inside cells, but a significant portion becomes heat. The heat spreads through your body because it has nowhere else to go. Even when you digest food slowly during rest, the overall effect is still an increase in entropy. Another part of the daily rhythm where entropy plays a major role is temperature regulation. If you feel cold and your body begins to shiver, those small muscle contractions are designed to produce heat by burning energy. The heat then spreads outward from your core to keep your internal organs at a stable temperature. Shivering is not random. It's your body compensating for the natural thermodynamic tendency toward losing heat. Without energy investment, your body temperature would drift toward equilibrium with the environment. Maintaining a stable internal temperature requires constant work because the natural direction of heat flow always moves from warmer areas to cooler ones. Every moment you remain warm in a colder space represents your body pushing against entropy locally while increasing it overall. As you move through the day, your brain becomes one of the largest sources of energy consumption. Even simple tasks like reading, thinking, listening, or remembering require electrical signals to travel between neurons. These signals depend on ion gradients across cell membranes. Establishing and maintaining these gradients requires pumping ions in specific directions, using energy from molecules like ATP. The pumping breaks down energy-rich molecules and releases heat. The brain stays active only by producing increasing amounts of entropy. Without these constant exchanges, the electrical activity that forms your thoughts would fade. Even when you're focusing intensely, your brain is releasing a steady stream of heat. You can feel this indirectly when your head feels warm after long periods of concentration. That warmth is the byproduct of neural activity. Neurons fire, ions move, and chemical reactions occur. All these interactions convert structured forms of energy into more dispersed forms. The brain maintains its internal organization by exchanging energy constantly, and the price of that order is the heat that spreads through your skull and eventually into the surrounding air. Over the course of a day, your muscles and brain work together to coordinate movements and actions. When you walk, your muscles convert chemical energy into motion, and your joints release heat from friction. The same thing happens when you lift objects, type on a keyboard, cook a meal, or even shift in a chair. Each action spreads energy and increases entropy. The body cannot move without generating heat because motion involves friction, and friction disperses energy into many microstates. That dispersed energy adds to the overall rise in entropy in your immediate environment. Your sense of hunger is also tied to entropy. When your energy reserves drop, the body seeks new sources of concentrated energy. Eating supplies that energy, but digestion breaks it down and redistributes it. The energy that once existed in tidy chemical bonds becomes part of a broader thermal landscape in your body. You use some of it to rebuild structures, but much of it leaves as heat. That balance keeps your metabolism running. Without continuing to import organized energy from food, the internal structures would eventually degrade because entropy would overwhelm the maintenance processes. As daylight turns into evening, your body's temperature naturally drops. This drop reflects changes in metabolism as your internal processes slow. The decline in temperature doesn't happen because your system stops producing heat altogether, but because the balance of energy shifts. Less energy is spent on movement, digestion slows, and the body prepares for rest. This cooled state still involves entropy. Heat continues to radiate outward. Your body continues to exchange energy with its surroundings. The difference is that the internal energy flow moves at a quieter pace. Your cells never fully pause, though. Even during sleep, mitochondria continue generating energy. Proteins maintain their shapes, and chemical reactions sustain essential functions. Entropy does not stop while you sleep. It simply moves through quieter pathways. Heat escapes your body into your bedding and the surrounding room. Your breathing slows, reducing the rate of gas exchange, but the diffusion of oxygen and carbon dioxide continues. The details differ from your waking state, but the fundamental processes remain consistent. Another area where entropy becomes visible is through the wear and tear your body experiences. Skin cells shed, hair grows and falls out. Old cells are replaced by new ones. Even though the body regenerates, these changes represent ongoing turnover driven by energy flow. The maintenance of structure requires continuous input. Without that input, the systems would drift toward more disordered states. That drift happens slowly but constantly, and your body compensates by rebuilding itself through countless biochemical reactions. Each repair requires breaking down molecules using energy and producing heat. The immune system follows similar principles. When you encounter pathogens, your body launches responses that require energy. White blood cells multiply, proteins rearrange, and chemical signals spread. Fighting infections increases entropy because it consumes energy and releases heat. Fevers raise your body temperature as metabolic processes accelerate. Even though it feels uncomfortable, the heat released during a fever reflects heightened entropy production as your body fights off something harmful. As you continue through daily activities, the clothing you wear also interacts with your body's energy flow. Insulation slows heat loss by trapping air around you. Without that insulation, heat would escape more quickly. Entropy would increase at a faster rate. Clothing doesn't stop entropy, it moderates the rate at which energy spreads. The same is true of blankets, shelter, and temperature control. Heating a home reduces the contrast between indoor and outdoor conditions, but maintaining that difference requires constant energy expenditure. The effort put into these systems is necessary because entropy always pushes toward uniformity. The food choices you make also influence entropy. High-energy foods provide more concentrated packets of chemical potential. When you consume them, your metabolism ramps up, increasing the rate at which energy spreads through your body. Lower-energy foods produce smaller effects but still contribute to the overall energy flow. Hydration operates similarly. Water helps facilitate chemical reactions that release or absorb energy. Without water, many reactions slow down, which can shift how your body handles heat. Even thirst reflects the body's need to maintain conditions that allow entropy-driven processes to flow smoothly. Your emotional state can be linked indirectly to entropy as well. Stress increases heart rate and muscle tension, requiring more energy. That increased energy use produces more heat. Relaxation reduces energy consumption, shifting the balance of heat production. Neither state violates thermodynamic principles. They simply reflect different rates of energy flow. The body adjusts constantly, balancing internal order with external disorder. At the cellular level, entropy influences how proteins fold. proteins form specific shapes, but their folding process depends on energy distribution. They collapse into structures that minimize energy and maximize stability within their environment. Misfolded proteins represent less favorable energy states. Repair systems correct them or break them down. These corrections require energy, which generates heat, increasing entropy externally. Even the most intricate biological mechanisms trace back to the simple principle that energy must flow through the system and will always spread where allowed. Your heartbeat is another rhythmic expression of entropy. Each contraction of the heart muscle requires energy. That energy originates from chemical reactions inside heart cells. As those reactions occur, heat is released. Blood carries warm fluid through the body, spreading energy. The regular beating spreads energy in a predictable pattern, but the underlying processes remain grounded in the same statistical tendencies that guide any energy distribution. Over the course of a full day, your body becomes a small-scale demonstration of entropy, increasing through countless small events. Eating, moving, thinking, digesting, breathing, healing, and sleeping all depend on converting concentrated energy sources into more diffuse forms. The order you maintain inside your cells and organs does not contradict entropy. It relies on continuous energy flow. Without constant energy input, the internal structures would drift toward states with fewer constraints. Your daily rhythm is shaped by these steady exchanges. When morning begins, energy use increases. During periods of rest, it decreases but never fully stops. Every moment involves microscopic interactions that shift the balance of energy. The pattern repeats without abrupt transitions because entropy operates steadily. The body adjusts its processes to maintain internal order while contributing to the overall rise in entropy outside itself. Most people don't stop to question why time feels like it moves forward instead of backward. Yet the reason behind that everyday experience is tied closely to entropy. We grow up assuming the passage of moments is built into reality, that the clock advances because it must, and that tomorrow will always follow today. But when you look closely at the laws of physics, you find something surprising. Many of those laws don't actually care about direction. On paper, they can run forward or backward with equal mathematical validity. Particles can collide in reverse just as easily as they collide in the usual direction, and the equations describing their motion still work. Yet in practice, we never see spilled milk gather itself back into a glass or a cooled drink become hot again without help. We never see footprints lift themselves out of sand. We never start a day younger than when we woke up. Something picks a direction for us. That something is entropy. To understand how entropy points time in a single direction, it helps to think of everyday experiences where the reversal of time would be unmistakable. Imagine dropping a glass onto a floor. The moment it hits, it shatters into pieces. The pieces scatter with unpredictable trajectories, bouncing and sliding until they come to rest. Every part of that motion seems completely natural. Now imagine watching that process in reverse. The fragments would begin sliding toward one another, leaping off the ground, assembling themselves into a perfect glass, and lifting back into your hand. Nothing in the individual laws of motion prevents that reversed scene. Yet it never happens. The reason it never happens is because the shattered state has vastly more possible microscopic arrangements than the original intact glass. It's overwhelmingly more probable. Entropy prefers the direction with more accessible outcomes, and that preference is what gives time a forward orientation. Another way to see this connection is by looking at heat. If you place your hand near a warm mug, heat flows into the cooler air around it. You never observe heat spontaneously leaving the air to make the mug even hotter. The direction of heat flow defines a before and after. The mug was hotter, then the air warmed slightly. The reverse never occurs on its own. The laws underlying the transfer of heat don't forbid the reverse, but the reverse would require an arrangement of molecular motions so precisely coordinated that it becomes effectively impossible. Entropy rises, and as it does, the sense of time moving forward emerges. You can see the same principle in something as small as a drop of dye falling into water. Once the drop spreads and blends, it never unmixes itself. The colour doesn't spontaneously form a perfect droplet again. When dye dissolves, it explores more possible positions than when it formed a concentrated blob. Entropy increases, and that increase gives the process a direction. The past is the moment when the dye was concentrated. The future is the moment when the dye is dispersed. The distinction between those two states creates a sense of flow. No matter how slowly you watch the mixing, the process only moves one way. This one-way movement is not just a property of liquids, heat, or broken objects. It appears in every natural system. Even the air in a room reveals this idea. If you spray a mist of fragrance into a space, the scent spreads until the concentration becomes uniform. You never experience the scent gathering itself back into a corner of the room without help. Once again, entropy increases as the molecules disperse, and that increase marks the direction of time. Before the spray, molecules were clustered. After the spray, they occupy far more positions. That difference gives meaning to the idea of before and after. From the standpoint of physics, nothing mystical decides the arrow of time. Instead, the arrow emerges from probability. Low entropy states are rare and fragile. High entropy states are common and robust. When a system is free to evolve, it moves toward states that are statistically easier to reach. Once it arrives there, the reverse would require an astronomically unlikely rearrangement of all particles involved. Time appears to flow forward because the universe continues shifting into more probable configurations. This plays out in your daily experiences in ways that are subtle but constant. If you leave a tidy space unattended, it tends to become slightly less tidy over time. Papers shift, dust accumulates, objects drift out of perfect alignment. Nothing in the room deliberately aims for disorder. These changes happen because there are more ways for the room to be untidy than perfectly arranged. Entropy increases, and with it, the room becomes less aligned with its earlier state. The progression from neat to slightly out of place is a simple demonstration of how time's arrow aligns with entropy's direction. The process also shows up in how memories form. Your brain records events by modifying the connections between neurons. Those modifications require energy, chemical reactions, and physical changes at the microscopic level. Because these changes occur in one direction, building new structures rather than spontaneously removing them, your experience of time is tied to these increasing alterations. You remember the past without remembering the future, because your brain's structure carries the imprint of previous states. The imprint can only form in one direction, because entropy dictates that chemical and energetic changes spread forward, not backward. Even aging is shaped by entropy. Over years, your cells experience gradual wear and accumulate molecular changes. Cellular repair systems can counteract some of these effects, but not all. The processes that maintain your body rely on continuous energy use to preserve internal structure. Over time, entropy exerts a steady influence, allowing certain changes to accumulate. These changes define a direction in your biological timeline. You were younger before and older now because numerous small entropy-driven shifts have layered over one another. The order of those changes forms a sequence that never reverses. This directional character of time becomes even clearer when you consider the early universe. At the beginning, the cosmos was in a relatively low entropy state despite its extreme temperature. The density and uniformity limited the number of ways matter and energy could be arranged. As the universe expanded and cooled, the number of available configurations increased dramatically. Galaxies formed, stars ignited, planets assembled, and complex structures emerged. All of these transitions represent entropy increasing. The arrow of time runs from a simpler early state toward a more varied and distributed later state. Everything that has happened, from the first atoms forming to the present moment, fits into that progression. If the early universe had begun in a high entropy state, time might not feel like it moves at all. There would be no gradient driving change. No direction would be favoured. Processes might fluctuate around equilibrium with no consistent drift. The sense of yesterday turning into today would not exist. The reason you can tell one moment from the next is that the cosmos began in a highly constrained arrangement that has been relaxing ever since. The direction of relaxation defines the arrow of time. This idea helps explain why the future feels open, but the past feels fixed. The past contains arrangements that have already taken place. Their entropy was lower. They involved more constraints. Those constraints left traces, physical records, memories, objects shaped by earlier events. The future, on the other hand, contains a vast number of possible high-entropy arrangements. Because the number of possibilities explodes as entropy grows, the future feels like a branching path. It's not that time itself branches, it's that entropy opens space for more outcomes than the narrow conditions of the past allowed. Another useful way to think about this is through information. A system with lower entropy carries more information about its precise arrangement. A deck of cards perfectly sorted has a clear order. A shuffled deck contains less specific information because it can exist in many configurations. When entropy increases, information becomes diluted. Over time, details fade, order disperses, and records are smudged by thermal noise or molecular motion. This decline in informational precision creates a one-way trend. You can track a procession of events from highly ordered beginnings toward more distributed ends. Entropy also shapes the arrow of time in technology. A smartphone battery discharges, a computer heats up during use, and a mechanical clock gradually wears down. These processes move in one direction, unless you supply energy to reverse them. Charging the battery, cooling the computer, or repairing the clock all require external work. Without that input, time continues forward for the device as entropy builds. Its components shift towards states with more possible arrangements. Nothing in the device spontaneously resets to a previous condition. The same principle applies in chemical reactions. Many reactions proceed in one direction unless energy is added to push them backward. Rust forming on metal, food spoiling, or colours fading in sunlight all reflect processes that move from lower entropy to higher entropy states. Reversing any of these naturally is unrealistic because the reverse state is so improbable. Entropy shapes the flow of chemical time by making certain transitions overwhelmingly more likely than their reverse. Even large-scale natural systems demonstrate the same directionality. Mountains erode as weathering breaks down their structures. Sand grains move from cliffs to beaches. Water flows downhill. Rivers carve deeper channels. All of these processes represent entropy increasing. Energy spreads, structures decay, materials disperse. The arrow of time embedded in landscapes is simply entropy pushing systems toward more probable configurations through countless small interactions. When you consider all these examples together, the connection between entropy and time becomes clear. Time feels like it moves forward because physical processes follow paths where entropy rises. If you could freeze entropy, time would lose its direction. Moments would blur together because nothing would distinguish before from after. It is the gradual and persistent climb of entropy that breaks this symmetry, giving time a slope to roll down. This perspective doesn't reduce the experience of time, instead it adds grounding. It shows that your sense of past, present, and future emerges from the same principles that govern heat, motion, mixing, and spreading. Entropy doesn't create time, it organizes it. The flow you perceive is a reflection of the universe shifting toward the states that are easiest to reach. Most conversations about entropy treat it as something tied only to heat, molecules, or the physical structure of matter. But a deeper look shows that information fits into the same framework. Every message, memory, record, or signal owes its stability to the arrangement of physical components. Letters printed on a page rely on ink patterns. Digital data relies on electric charges or magnetic states. human memories rely on neural connections. Each one of these arrangements lives in a world where entropy is always working, always nudging structures toward more probable configurations. When you follow this link closely, information stops feeling like something intangible or separate, and starts looking like an organized pattern embedded inside matter, constantly interacting with the forces that shape everything else. A helpful starting point is thinking about a simple written note. When you write a message on paper, the ink forms distinct shapes that encode meaning. Those shapes represent a highly organized arrangement. The paper could have countless patterns of molecules on its surface, but the message corresponds to only one of them. As long as the ink stays in the right place, the message remains readable. But the stability of that arrangement depends on conditions staying favorable. Heat, moisture, friction, or time can all disturb the pattern, smudging the ink or fading the lines. Each of those disturbances moves the system toward a state with more possible configurations, a more disordered one. When the ink spreads, the information becomes harder to read because the pattern holding it together has given way to a broader range of molecular arrangements. Entropy acts on the message by influencing the physical medium that stores it. Digital information follows the same principle, even though its storage seems more abstract. In a computer, data is stored using magnetic orientations, electrical charges, or transistor states. Each bit corresponds to a low entropy arrangement, where the system sits in one of two stable configurations. But that stability is not guaranteed forever. Heat causes electrons to move, radiation can disrupt patterns. Over long timescales, even solid-state memory devices experience errors. Storage technologies include error-correcting mechanisms precisely because entropy tends to disturb these arrangements. Your computer constantly expends energy checking, repairing, and resetting states to maintain the order needed for information to persist. Without that active maintenance, data would degrade slowly, becoming less reliable as random fluctuations alter the underlying physical arrangement. Biological information faces similar pressures. DNA strands store genetic instructions through sequences of nucleotides. Each sequence represents an ordered pattern that could be arranged in countless other ways. Mutations happen because thermal motion, radiation, or chemical interactions alter the arrangement. Most changes are neutral or small, and living organisms have repair systems that correct many errors. But the need for repair arises from the same thermodynamic pressures that drive entropy higher. Molecular structures naturally drift toward more probable states, unless energy is used to keep them organized. Life maintains its information because it spends energy doing so, not because information is magically exempt from entropy. Human memory illustrates this idea in a more personal way. A memory is not a fixed object stored in a single location. It is a pattern of strengthened connections, chemical states, and electrical pathways across networks of neurons. These structures require energy to maintain. They remain stable only if the supporting biochemistry continues functioning. Over time, without reinforcement, memories fade, synapses weaken, patterns soften. The entropy of the neural system rises because maintaining a specific arrangement demands continuous work. This is why repetition helps preserve memories. Repetition reinforces the structure, counteracting the tendency for the system to drift into more probable configurations where the original pattern is diluted. When you lose a memory, nothing breaks in a dramatic sense. Instead, the physical arrangement in the brain that once encoded the information gradually relaxes. The pattern that once distinguished that memory from countless other possible neural configurations becomes less defined. On the microscopic level, it reflects the unavoidable statistical trend toward more accessible states. The fading of information inside the brain is another form of entropy acting through physical structures. You can see these ideas in social or cultural information as well. Languages evolve because countless small interactions between speakers cause variations in pronunciation, grammar, and vocabulary. Over time, these variations accumulate. Some patterns become stable, others fade away. information stored in language drifts because there are many more ways for words to shift than for them to remain rigid across generations. Entropy doesn't act directly on language the way it acts on molecules, but the underlying principle remains. Systems with many interacting components naturally drift into states that permit more variability. Stabilizing information requires effort, whether through education, writing, or repeated communication. Libraries provide another example. Books degrade, paper yellows, ink fades. The information in those books remains accessible only as long as the physical materials resist entropy. Climate control, preservation techniques, and careful handling slow down the natural tendency toward disorder. Without these methods, written knowledge eventually becomes unreadable. Archives, museums, and servers all rely on energy-consuming systems that keep entropy in check locally so that information remains intact. The preservation of knowledge is always an active process. To see the connection even more clearly, consider how noise emerges in communication systems. When you speak into a microphone, the electrical signal representing your voice travels through wires or airwaves. Along the way, thermal fluctuations, interference, or imperfections introduce changes. These changes represent entropy's influence on the information stream. The signal contains structured patterns. Noise introduces randomness. The more random contributions accumulate, the less distinct the original information becomes. To counteract this, communication systems use amplifiers, filters, and error detection to correct or reduce the influence of noise. These corrections require energy, reinforcing the idea that maintaining information always requires work. A similar pattern appears when you think about images. A photograph is a frozen arrangement of pixels or chemical grains. It records details about a moment in time, but those details don't last indefinitely. Photographs left in sunlight fade as the chemicals break down. Digital images stored on devices degrade as storage media deteriorate. The system must continually expend energy to keep the stored pattern exact. Backups, redundant copies, and renewal processes all serve to reduce the influence of entropy on stored images. Without these measures, stored information drifts, becoming less accurate representations of the original moments. Even the act of remembering a piece of information during your day relies on resisting entropy. Neurons fire in patterns that reflect thoughts or memories. Those firing patterns draw energy. When the pattern repeats, your brain reinforces the connections involved, maintaining structure through constant biochemical activity. If you don't revisit a memory, the pattern gradually weakens. This weakening isn't a flaw. It reflects how information becomes less distinct as entropy increases. The brain compensates by strengthening important patterns through repetition, attention, or emotional significance. Every information system relies on physical organization. Whether it's a brain, a computer, a book, or a signal, the information exists because matter is arranged in specific ways. Entropy influences these systems by making certain configurations more stable and others more fragile. Highly structured arrangements require energy to build and maintain. Less structured arrangements arise naturally through random changes. The more complex or detailed the information, the more precise the physical arrangement must be, and the more vulnerable it becomes to entropy's influence. At a broader level, this connection between entropy and information helps explain why some processes feel irreversible. When something becomes disorganized, the information about its earlier arrangement becomes difficult to reconstruct. If you shuffle a deck of cards, the initial order is lost because the number of possible arrangements becomes enormous. Entropy increases, and the specific sequence that once existed becomes one among many possibilities. Without recording the sequence beforehand, you cannot restore it. The information isn't destroyed in a metaphysical sense, but it has become diluted among countless possible states. The system no longer contains the constraints that defined its earlier arrangement. This principle also underlies why lost data is so hard to recover. If a storage device becomes corrupted, the original arrangement of bits becomes scrambled or overwritten. Unless there is a backup or error-correcting system in place, the information cannot be reconstructed. The new arrangement has many more possible configurations than the original ordered pattern. Entropy increases, making the original state overwhelmingly unlikely. In physical terms, the process is not impossible to reverse, but it requires conditions so precise that they never occur naturally. In a broader sense, information can be thought of as the reduction of uncertainty. A message tells you which of many possible states the system actually occupies. Entropy measures how many possible states are available. When entropy rises, uncertainty increases because there are more possible configurations the system can take. Maintaining information means preserving distinctions between states. Entropy pushes against those distinctions, blending them together. The more organized the information, the more work must be done to resist that blending. This interaction becomes even clearer when considering how data compression functions. Compressing information means reducing redundancy, storing only the essential patterns. But the success of compression depends on predictability. Structured data compresses easily. Unstructured data does not. Entropy is a measure of unpredictability. High entropy data contains many possible patterns and cannot be compressed much without losing information. Low entropy data contains repetitive elements and can be heavily compressed. The relationship between entropy and information is not metaphorical. It is built into how information is quantified and stored. Similarly, encryption relies on increasing the entropy of a message. A well-encrypted message appears random because its structure has been transformed into a pattern with many possible interpretations. Only someone with the correct key can restore the structured pattern. Entropy plays a role in ensuring that the encrypted data does not reveal its underlying message. In this case, entropy becomes a tool for maintaining privacy. High entropy outputs are harder to distinguish from random noise. Information theory, born from studying communication, reveals that entropy is central to understanding how signals behave. The entropy of a message describes how much information it contains. Messages with many possible states carry more information, because receiving them reduces your uncertainty by a greater amount. But transmitting those messages reliably requires systems to counter the effects of noise. The more entropy a message has, the more vulnerable it becomes to disturbances, and the more energy and structure must be invested to preserve it. Even in the physical world, the concept of entropy helps explain why perfect records do not exist indefinitely. Microstates shift, molecules drift, heat spreads. Over enough time, every physical pattern degrades unless energy is continuously supplied to counter the drift. That is why ancient carvings fade, why digital archives require maintenance, and why memories distort. Information isn't immune to thermodynamics. It is woven into the same landscape as every other physical process. Understanding this relationship makes information feel more real, not less. Instead of being something abstract floating independently of matter, information becomes a grounded aspect of physical reality. Every thought, photograph, conversation, or memory originates from a physical arrangement that must constantly push against entropy to remain stable. When that push weakens, patterns blur, signals fade, and memories thin. This isn't a failure. It's the natural outcome of living in a universe where systems constantly move toward more probable configurations. Most descriptions of black holes focus on their intense gravity or the way they bend light. But one of the most surprising truths about them is how deeply they connect to entropy. At first glance, a black hole looks like the simplest object you could imagine. It has no visible surface, no intricate structure, and no way for light to escape. Everything that falls inside disappears from view. But appearances in physics can be misleading. Beneath that simplicity lies a level of entropy so enormous that it rewrites how we think about disorder, information, and the limits of physical knowledge. Black holes are places where the ordinary rules about energy spreading and systems drifting toward more probable states reach extremes that challenge intuition. A good way to begin understanding this is by considering how black holes form. When a massive star reaches the end of its life, it can no longer support itself with the fusion reactions occurring in its core. Fusion once provided an outward pressure that balanced the inward pull of gravity. When that process stops, nothing remains to counter gravity's force. The star collapses inward, compressing matter into an increasingly dense state. If the star is massive enough, this collapse continues until a point is reached where gravity becomes so strong that even light cannot escape. The region beyond which escape becomes impossible is called the event horizon. It acts as a boundary, not because it is a physical surface, but because it marks the limit of where signals can travel outward. This collapse might seem like a move toward greater order, because the matter becomes more compact. But the truth is far more subtle. Collapsing a star into a black hole actually increases the entropy of the universe dramatically. The reason lies in the number of possible internal configurations that can correspond to the black hole's external properties. Even though a black hole looks simple from the outside, the internal microstates that could exist inside it are numerous. The mass, charge, and spin are the only visible characteristics, but countless possible arrangements of whatever fell into it could exist behind the event horizon. This enormous number of internal states leads to an extreme entropy value. The surprising thing is that black hole entropy is not calculated from the matter inside in any direct way. It is instead encoded on the event horizon itself. Physicists discovered that the entropy of a black hole is proportional not to its volume, but to the surface area of its event horizon. This result, known as the Bekenstein-Hawking formula, was one of the most shocking findings in theoretical physics. It suggested that the information describing the internal states of a black hole is stored on its surface, as if the three-dimensional contents are somehow represented in two dimensions. This relationship hints at deep connections between gravity, thermodynamics, and information theory. The fact that black holes have temperature was equally surprising. At first, many believed that nothing could escape them, and therefore they must be completely cold. But Stephen Hawking showed that quantum effects near the event horizon allow black holes to emit radiation. This radiation, known as Hawking radiation, gives the black hole a temperature even though the interior is hidden from view. The temperature is inversely related to the mass of the black hole. Smaller black holes are hotter, larger ones are cooler, but no matter the size, the existence of temperature means that black holes obey thermodynamic laws, and like any system with temperature, they have entropy. This entropy dwarfs anything seen elsewhere in the universe. A black hole with the mass of the Sun has far more entropy than the Sun ever contained. The Sun's internal structure, its nuclear reactions, and its layer-by-layer complexity contain many microstates, but a black hole of equivalent mass has vastly more. This means that the collapse from star to black hole increases entropy exponentially. The black hole becomes a container of disorder so deep and vast that it overshadows any other form of entropy increase in the universe. Another remarkable aspect of black hole entropy is that it tells us something about the limits of information density. No physical system can store more information in a given region of space than a black hole can. If you tried to cram too much information into a small volume, the mass energy needed to do so would cause the region to collapse into a black hole. This leads to a principle known as the holographic limit. It states that the maximum information content in a region depends not on its volume, but on the area of its boundary. Black holes sit exactly at this limit. They show what happens when information is compressed to the maximum degree allowed by physics. At that point, no more detail can be added without forming a larger black hole. This connection between information and entropy becomes even more intriguing when you consider what happens to matter that falls into a black hole. From the outside, all information about its internal structure appears lost. Whether you drop in an encyclopedia, a diamond, or a cloud of gas, the resulting black hole is indistinguishable except for its total mass, spin, and charge. This raises a famous question called the information paradox. If information is supposed to be conserved in quantum physics, What happens to the details of what fell in? Does the black hole store them on its surface? Does the Hawking radiation somehow encode the information as it evaporates? Or does information genuinely vanish? The paradox isn't just a philosophical puzzle. It highlights the tension between the laws of quantum mechanics and the classical understanding of black holes. Quantum mechanics insists that information cannot be destroyed. Thermodynamics says entropy must increase. Black holes seem to do both at once, keeping entropy extremely high while hiding information. The resolution of this paradox may eventually reveal new physics beyond our current understanding. But what matters for entropy is the idea that black holes represent the ultimate form of disorder because they maximize the number of possible microstates consistent with their external appearance. This extreme entropy also influences how black holes behave over time. Although they seem permanent, black holes slowly lose mass by emitting Hawking radiation. This emission is incredibly slow for large black holes, taking far longer than the age of the universe. But the principle matters. Even black holes follow thermodynamic rules. They radiate energy because maintaining a system with a temperature above absolute zero requires energy to leak outward. As the black hole radiates, it shrinks. As it shrinks, its temperature increases. Eventually, if nothing replenishes it, the black hole will evaporate completely, releasing all of its mass as radiation. The final moments of this evaporation involve enormous increases in temperature and chaotic emissions of particles. The entropy continues rising throughout this process, even as the black hole disappears. When you consider black holes in the context of cosmic evolution, they serve as both sinks and sources of entropy. When matter collapses into a black hole, entropy leaps forward. During the slow evaporation, entropy continues to rise. Black holes accelerate the universe towards states with more possible microstates. Even the distribution of black holes across galaxies reflects this role. They swallow stars, gas, dust, and anything that crosses their event horizons. Every interaction between a black hole and surrounding matter contributes to the spread of energy and increases the complexity of the universe's thermodynamic behavior. At the center of most galaxies lies a supermassive black hole. These giants shape the environment around them. They influence star formation, heat surrounding gas, and regulate the growth of galaxies through energetic emissions and gravitational effects. Their presence alters the thermodynamic evolution of their galaxies because they serve as concentrated points where entropy becomes immense. The growth of a galaxy's central black hole is closely tied to how the galaxy matures. Energy emitted from matter falling into the black hole heats gas and prevents it from forming stars too quickly. This interplay ensures that entropy spreads through the galaxy in ways influenced by the black hole's immense pull. Even gravitational waves, a phenomenon discovered in recent years, play into this picture. When two black holes merge, they release a burst of gravitational energy that ripples through space. These waves carry information about the collision, but they also represent energy spreading into the universe. The merged black hole that remains has greater entropy than the two separate black holes had individually. The process fits perfectly with the second law of thermodynamics. Two ordered systems combine into a single system with a larger event horizon surface area and therefore more entropy. This reveals something subtle but important. Entropy doesn't simply measure disorder in the everyday sense. In black holes, entropy measures the limits of what can be known. A black hole hides its internal details behind an event horizon, but those hidden possibilities contribute to the vast number of microstates that define its entropy. The more massive the black hole, the larger the surface area of its horizon and the higher its entropy. This means that as matter accumulates around the universe and collapses into black holes, the overall entropy grows not just because energy spreads, but because the universe gains more surfaces that encode enormous amounts of potential internal configurations. Black holes also provide insight into the deep relationship between space, time, and thermodynamics. The discovery that black hole entropy scales with surface area rather than volume suggests that spacetime itself may have a similar property. Some theories propose that the fabric of space may work like a hologram where information about a region exists on its boundary rather than inside it. This idea remains part of active research, but it underscores how black holes push the boundaries of thermodynamics, showing that entropy is not just a property of matter, but may be tied to the geometry of space. When thinking about entropy at extreme levels, it's helpful to compare black holes with other structures in the universe. A star has significant entropy because of its internal heat and motion. A cloud of gas has greater entropy because it can occupy many configurations, but nothing matches the entropy of a black hole. A single black hole contains more entropy than entire galaxies full of stars. The difference lies in the number of possible internal arrangements that correspond to identical external features. Since a black hole has few visible properties, all the hidden variations accumulate as entropy. This means that the universe's long-term future may be strongly linked to black holes. As matter collapses into black holes and those black holes interact or merge, the entropy of the universe climbs. Eventually, over vast timescales, black holes will evaporate, releasing entropy through radiation. The universe will continue inching towards states where energy is more evenly distributed and structures are less distinct. Black holes accelerate this trend by taking concentrated matter and turning it into something with vastly more possible microstates. Understanding black holes from the standpoint of entropy changes the way they feel. Instead of viewing them only as destructive objects, you can see them as extreme engines of thermodynamic evolution. They take order, concentrate it, and transform it into something containing far more potential configurations. They expand the number of ways matter and energy can exist. Their presence in the universe is not an exception to the second law. It is an amplification of it. Many people hear about entropy increasing and assume it means everything is slowly winding down towards some bleak ending. The phrase itself often gets misinterpreted as a sign that the universe is running out of energy or drifting into a state where nothing meaningful can happen. But when you look closely at what entropy actually describes, that picture becomes far too narrow. Rising entropy does not mean fading in the way most people imagine. It doesn't represent a loss of richness or a collapse of potential. Instead, it points to a shift in how energy moves and how systems evolve, and that shift is responsible for nearly all of the complexity we see around us. To understand why entropy does not simply mean decline, it helps to think about processes that clearly involve rising entropy, yet produce structures, patterns, or events that feel vibrant rather than weary. Consider the way clouds form in the sky. Warm air rises, cools, and releases moisture that condenses into droplets. The droplets cluster into the shapes we recognize as clouds. The process depends entirely on the redistribution of energy. Heat spreads, moisture diffuses, and air currents shift. Entropy increases throughout the entire sequence, but the result is not emptiness. The result is a dynamic atmosphere full of motion and structure. A similar pattern appears when stars form. Vast clouds of gas begin with high entropy because the particles are scattered widely and can occupy many configurations. As gravity pulls them inward, the cloud contracts. At first glance, this contraction might seem like entropy decreasing because matter becomes more concentrated, but the key is in the energy released during the collapse. As the cloud compacts, gravitational energy transforms into heat which radiates outward. That spread of energy dramatically increases entropy. The cloud becomes a star not by defying thermodynamics, but by following it. The rise in entropy makes the formation possible by allowing energy to escape in enormous amounts. The structure that emerges is a star, bright, hot, full of activity. Not a fading shell, but a powerful outcome of increasing entropy. Even everyday life shows that entropy and vibrancy coexist constantly. When you cook a meal, the process involves energy spreading from heat sources into food. Molecules gain energy, move faster, react, and transform. Flavors develop. Textures change. entropy increases through these transformations. Yet the result is not decay, it is creation. Rising entropy supports the emergence of patterns rather than erasing them outright. The same is true when you listen to music. The sound waves travel outward, dispersing energy through the air. Entropy rises as the sound fades into the background, but the experience itself depends on energy spreading in precise ways. This subtle relationship between entropy and creativity appears from the smallest systems to the largest. It becomes especially clear when discussing living organisms. Life does not exist in spite of entropy. It exists because of it. Organisms maintain internal structure by continually consuming energy and releasing heat. This increase in external entropy allows internal order to persist. The warmth your body generates is a direct result of metabolic reactions that convert concentrated chemical energy into more dispersed forms. The rise in entropy outside your body is what sustains the structured complexity inside it. Without that flow, life would not function. This idea extends into evolution as well. Life's diversity arises because energy moves through ecosystems in uneven, dynamic ways. Sunlight excites electrons in plants. Nutrients cycle through food chains. Heat dissipates. Each of these interactions increases entropy in the broader environment, yet they also create opportunities for new forms of life to emerge. Rising entropy doesn't drain potential. It expands the range of paths a system can explore. So why does entropy often get described as the force behind decay or fading? One reason is that people tend to associate disorder with breakdown. When a building crumbles, when metal rusts, when food spoils, entropy is clearly involved. These examples are easy to visualize, and they fit the intuitive idea of disorder increasing. But these familiar images don't capture the entire picture. They only show one side of how entropy interacts with matter. They show what happens when a system loses access to energy flows that maintain structure. When energy no longer enters the system, existing structures degrade. That degradation is not caused by entropy itself. It is caused by lack of input. The difference is subtle, but important. To see that distinction, think about a refrigerator. When it's running, it keeps its interior cold by pumping heat out and expelling it into the surrounding room. Inside the refrigerator, entropy goes down because the machine expends energy to maintain low temperatures. Outside the refrigerator, entropy increases because warm air spreads. Now imagine unplugging it. Without the flow of energy, the interior warms up. Entropy rises inside because the system can no longer sustain the structured state it once had. The fading of the cold environment isn't caused by entropy acting destructively. It's caused by the absence of energy counteracting entropy locally. The same principle applies to living organisms. When an organism stops acquiring energy, its internal structures eventually break down. Cells lose their ability to maintain the specific molecular arrangements required for life. This breakdown is not entropy squeezing out complexity. It is the system no longer receiving the energy needed to resist the natural drift toward more probable configurations. Entropy does not destroy structure planlessly. It simply fills the space left behind when energy stops reinforcing patterns. This perspective makes it easier to understand the long-term evolution of the universe. As stars burn their fuel, they radiate energy outward. This radiation increases entropy in the cosmos. It doesn't make the universe fade instantly. Instead, it enables billions of years of star formation, planetary systems, chemical cycles, and events that depend entirely on energy flowing from hot objects into colder surroundings. Entropy rising does not strip the universe of meaning or activity. It provides the backdrop against which activity unfolds. The idea of a heat death of the universe often leads people to imagine an empty, silent darkness where nothing remains. This description can sound bleak, but it's important to remember that this scenario lies an unimaginable distance in the future, and even then, entropy increasing does not mean everything suddenly vanishes. It simply means that energy sources become too evenly distributed to support the kind of processes that require gradients, like stars shining or living organisms functioning. The universe would still exist. It would simply lack the free energy necessary for the structures we're familiar with. Entropy rising is not a destructive force taking something away. It's a natural process that gradually levels the landscape of energy over incomprehensibly long timescales. Another misconception is that entropy represents a kind of universal decline in complexity. This isn't accurate. Complexity can arise even in high entropy environments if energy flows continue to move through the system. Hurricanes form in warm oceans, even though the surrounding atmosphere has higher entropy than the ocean surface. Planetary rings can self-organize into stable structures because they continually shed energy through collisions. Even galaxies form spiral patterns despite the underlying rise in entropy. These structures do not violate thermodynamics. They rely on processes that produce net increases in entropy globally, while creating temporary order in local regions. This interplay between local order and global disorder is essential to understanding why entropy does not signal fading. When energy flows from one region to another, it can create hotspots of organization. A candle flame is a highly structured phenomenon. It has a distinct shape, layered temperature regions, and predictable behavior. Yet it exists only because the candle wax is burning, releasing heat, spreading energy, and increasing entropy overall. The flame is a complex outcome of rising entropy, not a contradiction of it. You can think of entropy as permitting structure rather than forbidding it. It defines the direction in which structure can form. Patterns require energy flow. Entropy ensures that this energy moves in consistent ways, always from concentrated sources toward more dispersed arrangements. As long as sources of concentrated energy exist, complexity can continue to appear. That principle is what allows planets to have weather systems, stars to shine, life to flourish, and chemical reactions to proceed. When entropy rises, the universe broadens the landscape of possible outcomes. Some outcomes include structures, others include decay. Both are part of the same overall movement toward more distributed energy. This broader understanding also helps explain why entropy is sometimes described as a measure of ignorance. As a system becomes more disordered, it becomes harder to specify exactly what state it's in. There are more possibilities, but more possibilities do not always mean less richness. In many cases, they allow for more dynamic behavior. A gas cloud with high entropy can behave in countless ways and can collapse, interact, spread, or support the formation of stars. A low-entropy system is highly constrained and has fewer paths available. The expansion of possibilities is part of the universe's ongoing evolution. It's also worth noting that entropy rising does not erase everything. It doesn't obliterate records, memories, or structures instantly. These things degrade slowly as energy flows weaken or conditions change. The stars we see today formed billions of years after the universe's birth because entropy had risen enough to allow conditions for star formation. Rising entropy opened new pathways rather than closing them. It transformed a uniform early universe into a diverse one full of galaxies and planets. In human experience, the idea of things fading often comes from personal senses of loss or change, but entropy doesn't operate with intent. It doesn't choose decline. It simply describes how systems evolve when left to themselves. Humans often need to supply energy to maintain order, because our survival requires certain structures to remain stable. When those structures naturally break down without energy input, the resulting changes might feel like fading. But entropy is the backdrop for all experiences, not a force opposing them. When you step back and consider the entire picture, entropy does not represent fading. It represents transformation. The universe shifts from constrained, narrow states into broader, richer states. These shifts create opportunities for structure to emerge and for processes to unfold. They also limit how long certain forms can persist without energy flow, but that doesn't make entropy an enemy of complexity. It makes it the framework within which complexity arises and dissolves. Some ideas settle into your thinking not because they are loud or dramatic, but because they invite you to pause and look at ordinary life from a slightly different angle. Entropy is one of those ideas. After exploring it across the scales of the universe, from ice cubes to stars, from the body's quiet cycles to the depths of black holes, it becomes natural to turn inward and consider what all this disorder means for your daily experience. Not in a theoretical way, but in a personal, practical way. There's something calming about seeing a principle so universal, reflected in the small movements of your own routine, your habits, your surroundings, and even the gentle flow of your thoughts. It doesn't require anything cosmic to bring entropy into focus. It shows up in places so familiar that you don't need to search for it at all. Think about the way a day unfolds from morning to night. You begin with intentions, maybe a plan or a sense of direction. You might start with a clean workspace, a tidy table, or a freshly made bed. As the hours pass, the space around you changes. A mug ends up beside the sink. A notepad sits open with scribbles from a conversation you had. A pair of shoes lands near the doorway after a walk. These shifts aren't mistakes. They're a reflection of activity, motion, thought, and effort moving through time. Entropy increases not because things are falling apart, but because you're interacting with your environment in countless small ways. Each interaction widens the range of possible states your surroundings can take. Instead of signaling decline, these variations reveal that life is happening. There is a gentleness in understanding that your environment naturally drifts unless you guide it. The drift isn't a judgment about you or your habits, it's a statistical reality. Everything you touch has many more possible ways to end up slightly misaligned than perfectly placed. Once you see that, the pressure to keep every corner controlled begins to soften. You may still tidy, clean, and organize, but you do it knowing you're choosing to impose order temporarily, not expecting order to exist on its own. That shift can make maintenance feel less like an obligation and more like an intentional moment of care. You work with the natural tendencies of your space instead of fighting against them. Entropy also helps explain why routines can feel both comforting and fragile. A routine is a low entropy structure. It relies on repeated patterns, predictable steps, and consistent energy input. But life rarely stays still. New responsibilities appear. Unexpected events shift your schedule. Small interruptions accumulate. The routine drifts because anything structured requires energy to maintain. Recognizing this brings a sense of relief. When a routine begins to slip, it doesn't mean you've failed. It simply means the system is behaving as any system behaves without deliberate reinforcement. This understanding opens the door to a kinder relationship with yourself. You can remake routines when needed, adjust them when they change, and rebuild them without believing something is wrong. Entropy invites you to accept that structure will always need tending, whether it's a morning ritual, a workspace, or a habit you value. Order grows through effort. Disorder grows naturally. Knowing that doesn't discourage improvement. It makes improvement feel more aligned with reality. The same principle applies to your thoughts. Minds are not static. They shift with experience, with emotion, with memory, and with information. Thoughts wander because the brain contains countless pathways for associations to form. When you try to focus on something important, energy is required to maintain that focus. Without intentional effort, attention dissolves into wider possibilities. That tendency isn't a flaw, it's the mind behaving in accordance with physics. The brain is not a rigid structure, it's a dynamic system where patterns form, fade, reappear, and transform as energy flows through neurons. This makes lapses in concentration easier to understand. A wandering mind is not disobedient. It is exploring many states because that exploration is natural. Focus simply narrows the system into a smaller region of possibility, and maintaining that narrowing takes effort. When the effort wavers, attention expands again. The drift is not a personal failing. It's the thermodynamic reality of a system with enormous complexity and constant flow. Recognizing this allows you to return to focus without frustration. Each return is simply the act of applying energy to bring the mind back to a narrower pathway. Entropy also shows up in relationships. Over time, friendships and connections evolve because people grow, move, change, and experience life in different directions. The initial structure of a relationship may feel solid, but without ongoing effort, messages, shared moments, conversations, care, connections naturally loosen. This loosening isn't an inevitable decline. It is the result of systems drifting when energy stops flowing through them. Relationships thrive when energy continues to circulate in small but meaningful forms. Seeing this through the lens of entropy can help remove the feeling that distance or change is a sign of something wrong. Instead, it becomes clear that closeness emerges from sustained attention, not by default. The concept also plays out in decisions. When you have many possible choices, the system, your mind, exists in a high entropy state because there are numerous ways the future could unfold. Narrowing that range by making a decision reduces uncertainty, effectively moving to a smaller set of possible outcomes. But maintaining clarity requires energy. Doubt, reconsideration, and distraction slowly widen the field of possibilities again unless you reaffirm or adjust your direction. This doesn't make decision-making fragile, it makes it dynamic. The balance between clarity and uncertainty mirrors the balance between order and disorder everywhere else. In a larger sense, entropy offers a frame for understanding why things feel transient. Objects age, paint fades, materials weaken, food spoils. These changes occur because the structured arrangement of molecules becomes harder to maintain as time passes. But these processes don't signify that the universe is erasing meaning. They show that time leaves imprints because systems evolve through energy flows. Every form carries the story of how it interacted with its surroundings. Fading ink, shifting colours, and worn surfaces are records of those interactions. They don't diminish the significance of the object. They reveal its relationship with time. Entropy also sheds light on why moments feel precious. A moment is a configuration of your thoughts, surroundings, and circumstances that will never occur again in exactly the same way. Not because time destroys it, but because there are countless possible ways for things to move forward, and only one precise arrangement that produced the moment you're experiencing. Entropy ensures that future states are broader in possibility. The uniqueness of a moment arises because low entropy configurations are narrow and fleeting. But that fleetingness doesn't reduce their value, it amplifies it, reminding you that experiences are temporary because systems evolve continuously. This perspective can help with letting go. When a day ends differently than expected, when plans change, or when something doesn't unfold the way you hoped, entropy provides a gentle explanation. Systems move toward broader possibilities. That movement can bring unexpected paths, new opportunities, or rearrangements you didn't anticipate. You can guide parts of your life, but you can't hold everything in a narrow pattern forever. Understanding this makes it easier to adapt instead of resisting every shift. Entropy influences how you rest too. Rest doesn't come merely from slowing down. It comes from reducing the number of directions your mind or environment can pull you. When you rest, you lower the energy you spend organizing your thoughts or surroundings. You allow the system to settle. This settling isn't decline, it's recalibration. Rest gives your internal processes space to redistribute energy, repair structures, and restore balance. Entropy doesn't conflict with rest, it guides the need for it. When you think about creativity, the connection deepens. Creativity emerges from exploring many mental states and combining them in new ways. High entropy in thought allows new ideas to surface because the system isn't locked into a rigid pattern. But creativity also requires moments of narrowing where ideas take shape and become coherent. This movement between open possibility and structured expression mirrors the thermodynamic balance between disorder and order. Creativity thrives because the mind shifts naturally between these states. Entropy also influences how people understand meaning. Meaning emerges from patterns, memory, context, narrative, intention. Maintaining these patterns requires mental energy. When emotions fluctuate or when life becomes overwhelming, meaning can feel blurry. That blurriness isn't emptiness. It's the system exploring too many possibilities at once. With rest, reflection, or connection, the pattern tightens again. Meaning becomes clearer because the mind regains the energy to sustain structure. In relationships with the world, entropy shapes how you experience change. Seasons shift, weather patterns fluctuate, trees lose leaves, rivers carve new paths. These changes reflect energy flowing through the environment. Entropy drives these flows, yet the result is not monotony. It is variety. The world doesn't fade as entropy rises, it evolves. Each cycle of change reveals another layer of how systems respond to conditions. Entropy also influences how you understand imperfection. Perfect symmetry, perfect order, perfect alignment. These are low entropy states with very few possible configurations. They are rare and require continuous effort. Imperfection, by contrast, is natural because it encompasses countless possible arrangements. Slight variations aren't flaws. They are signs that the system is living, moving, interacting. Accepting small imperfections in your surroundings, habits, and self becomes easier when you recognize that perfection is not the natural state. Entropy makes variation the norm. This perspective also encourages patience. When a task becomes messy, a plan changes shape, or a project wanders through unexpected turns, entropy offers a reason rooted in how systems behave. Things drift because drift is the natural tendency. Reshaping them takes energy and attention. That investment doesn't need to be rushed. It can be slow, gentle, and steady. Understanding entropy makes the process feel less like a fight and more like a collaboration with the natural behavior of systems. One of the quietest lessons entropy provides is that order and disorder are not opposites in conflict. They are partners. Order emerges where energy flows in focused ways. Disorder grows where energy spreads. Both movements shape your environment and your experience. You impose order when needed, let things drift when appropriate, and rebuild when the time feels right. Entropy doesn't dictate which path to choose. It explains why each path behaves the way it does. Ultimately, entropy offers a framework for understanding your life, not as a battle against disorder, but as a steady negotiation with the natural tendencies of the world. It reminds you that nothing stays fixed and that this flux is not harmful. It is the backdrop that makes growth, change, and experience possible. Disorder doesn't erase what matters. It shapes the environment where meaning forms. Embracing this view allows you to move through life with more flexibility, more kindness toward yourself, and more ease in navigating the natural flow of your surroundings.